Shall we start, ma'am?
Ma'am, please wait, ma'am.
We will start our program shortly.
Yes, ma'am.
Ma'am, shall we start?
Yes. Good afternoon, Dr. Rajabhubadi.
Good afternoon, madam.
Good afternoon.
How are you, sir?
Yeah, I'm fine, madam.
Yeah.
My voice is audible? Is okay?
Yes.
Okay, fine.
Ma'am, start.
Yes. Okay, ma'am. Good afternoon to all. I welcome you all Day 3, Session 6 of the Virtual International Conference on Hierarchically Structured Material 2021, organized by Department of Physics, SRM Institute of Science and Technology, Ramapuram campus. In this session, we are having our first invited speaker, Dr. Rajabhupati Mani, Department of Chemical and Metallurgy Engineering, School of Chemical Engineering, Aalto University, Finland. He is going to speak on mesocrystal nanoparticle as building block in a single crystal. Now I request Dr. Sarunan, Assistant Professor, Department of Physics, SRM Institute of Science and Technology, to introduce our speaker to participants. Sir. Sarunan, sir. Dr. Sarunan. Sir, please introduce our speaker.
Yes, ma'am. Yes. Am I audible?
Yes.
Yes, sir.
Yes.
Very good afternoon to all. It's my pleasure to introduce Dr. Rajabhupati Mani from Mary's Curie Postdoctoral Researcher, Department of Chemical and Metallurgical Engineering, School of Chemical Engineering, Aalto University, Finland. Okay. Dr. Rajabhupati completed his PhD from the Department of Physics, Periyar University, Salem. After completing his PhD, he was there in Ramapuram University of Technology, Department of Chemical Technology, as a PhD research exchange program under the Indo-Finnish scholarship. And then he was there in the same university as a visiting researcher by the year 2014 to November 2014 to December 2014. And after completing that, he switched over to as a postdoctoral researcher, type A, at Shandong University, CIS State Key Laboratory of Crystal Materials, Jinan, China. And this is from the year January 2016 to June 2018. After completing that, he switched over to Priest University, Priest University, Center for Research and Development, Priest University, Tanjavur, Tamil Nadu. He was there as a short-term period, right from January 2019 to September 2019 as an assistant professor. So after all completing this, right now he is Mary Curie postdoctoral researcher at Aalto University, School of Chemical Engineering, Department of Chemical and Metallurgical Engineering, Finland. Okay. So his core area of research is studies on mesocrystals and microstructural analysis using cryotherm and tomography, structural analysis of lanthanide doped nanoparticles for light emitting diode applications, growth of co-crystals, salt and polymorphism, organic crystals for OLED application based on molecular design, growth of NLO crystals for optoelectronic applications, and terahertz generation. So far, Dr. Rajabhupati has published 23 publications in well-reputed journals, and that includes Chemical, European Journal, Inorganic Chemistry, Journal of Physics and Chemistry, and Crystal Engineering Communications, etc. Okay. So he has a total citation of 201, and the H index is up to 9. He is a life member of Materials Research Society of India since 2020, and life member of Mary Curie Alumni Association since 2019, and also life member of Indian Association for Crystal Growth right from 2010 onwards. Okay. So with this short introduction, now I requested Dr. Rajabhupati Mani to present his research findings. Sir, the session is yours. So please carry on. Thank you very much.
Yeah. Thank you, Dr. Saravanan, for the nice introduction.
Yeah.
So shall I share my screen now?
Yes, sir. You can share
Yes.
your screen.
Yes.
Okay. So good afternoon to all. First of all, I would like to thank the management of SRM Institute of Science and Technology for giving this opportunity to share my knowledge and expertise with you through this e-conference. I thank the convener of this conference, Professor L. Sudha, the organizing secretary, Dr. M. Saravanan, the coordinator, Dr. B. T. Beena, and organizing committee members, SRM Institute of Science and Technology, Ramapuram campus, Chennai, for organizing this great international event during this pandemic. So my title of my talk is mesocrystals. Title of my talk is mesocrystals. Nanoparticle as a building block in single crystals. As Dr. Saravanan introduced me, I'm Dr. Rajabhubadi Mani, working as Mary Curie postdoctoral researcher in Aalto University, Finland. A small introduction to Aalto University. Aalto University is located in Helsinki. It is the capital of Finland. Finland is sharing borders with Sweden, Norway, Estonia, and Russia. Finland population is about 5.5 million. Even the population is less than Chennai population, I hope. And this Aalto University is the second largest university in Finland and holding world rank around 120. Finland is best known for Nokia, and also best for they have best school education system in this world. And Finland is one among the top happiest countries in this world. Now it is 4 years in a row. And there are other things like the first commercial SMS was sent from here. The Linux operating system was created by Finnish, and now we are having 5G network. So the title is mesocrystals, nanoparticle as a building block in single crystals. The word mesocrystals may be new for some of you because it was coined or termed a decade ago, and still basic research is going on at the molecular level. Mesocrystal is a kind of intermediate between bulk single crystals and nanoparticle in terms of its size. You are so familiar about what is single crystals and what is nanoparticle. It is an intermediate in terms of its size. The mesocrystal size is about a micron. So the crystal growth is a very old technique, and we are applying classical growth model to explain the formation of nucleus, the growth of crystals, etc. But there are some crystals with complex morphology. For example, hierarchical structure, the main theme of this conference. We cannot apply this classical crystallization model. So we are in need of another theory, a crystallization theory. We call it is a non-classical crystallization. The way we came from classical physics to quantum physics, classical optics to quantum optics, we need some other theory to explain the crystals with the complex morphology. We call it is non-classical crystallization. The mesocrystals comes under non-classical crystallization. Also, all the hierarchical structure materials are coming under non-classical crystallization. In this era, we have so many sophisticated analytical instrument facilities available nowadays to see what is happening inside the solution. So with this advantage of techniques, different techniques, the research has been developing nowadays, and already mesocrystals are applying for different applications. So the outline of my talk is what is a classical approach, how to use a classical theory to grow the crystals, or to explain the crystals to the formation of nucleus. What is non-classical approach? What is mesocrystals? What is a hierarchical structure? And what is oriented attachment? What are the difference among them? And then applications of mesocrystals in different field. For example, we can use mesocrystal as a photocatalyst. We can use as electrode in battery and capacitors. We can use mesocrystal in sensors and pharmaceutics. So before going to see what is mesocrystals, what is non-classical crystallization, I would like to put a question to you that this is the image of a apple, a cross-sectional image of apple, and this is a pomegranate. See, when we see the apple, it is completely made up of flesh. But here in the pomegranate, there are beads. It is not made up of flesh, but brood beads, or we can say small particles. Here in the orange, also there are brood beads or fruit particles, but it has some orientation. Also, it has a different domain, and it has some well-defined boundaries. So, do we have similar internal structure in single crystals? And can it influence the properties? So, just to think about it, you can find the answer in the upcoming slides. So, when we walk on the beach, you might have seen this seashell. I'm sorry for this image. If any non-vegetarian is here, vegetarian is here. So this is a PL, which is covered by a hard material. We call it is nacre. Actually, it is very strong material. As you know, PL is the only ornament produced through a biological process. So we need to cover with a strong material. We call it is nacre. Actually, nacre is a kind of crystalline substance composed of crystallized calcium carbonate and organic protein conchyline. It is very strong, resilient, and iridescent. If you tilt this material, you can see different colors. So it is a very strong material because it has a stacked layer of calcium carbonate with a soft organic material in between the calcium carbonate stacked layer. This is the perfect example for mesocrystals. We can say this mesocrystal is a composite. It is not composite like a concrete composite because the ingredients are in macroscopic level. Mesocrystal, we can say it is a nanocomposite because the organic and the inorganic materials are organic materials are the constituents are in molecular level. So we can say it is a nanocomposite. So, and the recent study find that this is a SEM image of this nacre, where you can see clearly the plate looks like the plate-like materials are calcium carbonate, and in between the plate there is a gap which is actually filled by organic conchyline materials. So that's why due to this arrangement, this material is very strong. So before going to see non-classical crystallization, I would like to quickly recall you what is a classical crystallization, how we are applying this classical crystal growth model to explain the crystallization. To prepare crystals, we need to prepare supersaturated solution. To prepare supersaturated solution, we need to prepare undersaturated solutions. With these undersaturated solutions, if you cool the solution, or if you heat or evaporation, or if you put some anti-solvent, a poor solvent, you can get supersaturated solutions. From the supersaturated solution, we can get crystals. From the solubility curve, we can determine whether the solution is undersaturated or supersaturated. This is an undersaturated region. This is supersaturated region. This is the metastable zone. This is unstable zone. We can get bulk single crystal here. Suppose your solution is here, you cannot get any crystals. Suppose your solution is highly supersaturated, you can get crystals, but the crystals are mostly polycrystals. So if you reach, for example, if your undersaturated solution is here, if you cool down, you will reach the metastable zone. If your undersaturated solution is here, if you cool down, you will reach supersaturated region. So based on where you are going, you will get a bulk single crystals or polycrystals. There is a crystallization is actually a phase transformation process. So after you form the supersaturated solution, there are some nucleation cluster with the radius r. So after form the nucleation cluster, and the Gibbs free energy in the system will change. This is the change in Gibbs free energy. Actually, after form the nucleation cluster, the Gibbs free energy will decrease. When it is in low temperature, for the liquid, the Gibbs free energy is high. After form the cluster, the Gibbs free energy will decrease. So this is the Gibbs free energy decrease, which is equal to 4/3 pi r cube Gs minus Gl. Gs is Gibbs free energy of solid and Gibbs free energy of liquid. So here I'm assuming this nucleation cluster is radius sphere. So I'm using 4/3 pi r cube. If it is cube or if it is a rectangle, you can use according to the size of nucleation cluster. So after form the nucleation cluster, there is a interfacial energy between the solid and the liquid. Liquid means supersaturated solution. The interfacial energy is a kind of external energy, which suppress the growth, crystal growth. You can assume that the interfacial energy is a kind of surface tension in the liquid. So actually it is suppress the growth. So since it is suppressing the growth, the Gibbs free energy of the system will increase. So this is the Gibbs free energy. Actually, it suppress the growth. So it is we should reduce the Gibbs surface free energy to grow bulk crystals or to get a nucleus from the nucleation cluster. So this is the total Gibbs free energy change. When the nucleation cluster reach a critical radius, the crystal will start to grow. And this is the total Gibbs free energy of the system. So when you differentiate this equation at r equal to r star, you can get a critical radius. After reach the critical radius, the nucleus form a crystals. So this Gibbs free energy is actually barrier in a crystal growth, and we need some driving force to get a bulk crystals. So we can say simply the crystal growth is a competition between surface free energy and the bulk energy term. In the bulk energy term, actually we got from chemical potential. So it is a kind of competition between these two. If the Gibbs free energy is very high, you cannot get any crystals, because in the nucleation cluster won't reach the critical radius, you cannot get crystals. So this is the theory, and we are applying two models to explain the further growth of nucleus. One is a Kossel-Stransky growth model, or we can say layer by layer growth, and this one is spiral growth. So in this layer by layer growth, after form the nucleus, there may be kink site, positive kink, negative kink, or there are adsorbed molecules, and based on the surface free energy or based on the Gibbs free energy of the system, the next layer or next molecule will attach here or attach here. So we can say addition of atom by atom or addition of molecule by molecule, or simply we can say this is a layer by layer growth. So in this spiral growth model, there may be some screw dislocation. Actually, this screw dislocation trigger the growth to form a next layer. So the crystal will grow like the crystal will grow like a spiral growth. We can say it is a spiral growth model. So this is another natural mesocrystals, sea urchin spine. It gives a different spike. This is the broken SEM image of broken spike, where you can see this is the crystals. This is the crystals. In between them, there is a gap which is filled by some other non-crystalline material. So here, the non-crystalline material is calcium carbonate, and the crystalline material is also calcium carbonate. If it is a completely pure single crystals, when you break the crystals, the cleavage plane is very clean. But here, the cleavage plane is not clean. It is not very smooth. So we can say that this spike is not only made up of pure crystal material. There are some other entity between the crystal. We call it is here. It is a amorphous calcium carbonate. In the previous example, nacre, and the another entity is concaline organic protein. So these are the examples for mesocrystals. And again, this is a non-classical growth. So what we saw is a classical growth model. We are going to see non-classical growth. In the classical growth model, after form the supersaturated solution, nucleation is the first step. Once we get a supersaturated solution, we can get some nucleus. Nucleation is the first step. But here in the case of non-classical growth, after form the undersaturated solution, your solution will get tensed. This is the undersaturated solution. Your solution will get tensed here. Then there is a nucleation cluster. So based on the stability, it will go tensed liquid or it will go nucleation cluster. Again, it will go the nucleus. This is the nucleus. So there is a, based on the stability, it will go either side. After form the nucleus, you can get a bulk single crystals. So it is actually before form the nucleation cluster, there is a tensed liquid state. So we can call it is a two-step process, not a one-step process. It is a two-step process. But in the case of classical, after form the supersaturated solution, we can get a nucleus. So here, for example, this is the dilute solution. The clusters are attaching together, and again it is attaching, but the attachment is a kind of randomly attached here, but it gives some orientation. So from this orientation, you can get some structure. So here, this is the nucleus. This is the nucleus. So if it is classical, after form the solution, you will reach here. It is a one-step process, but here it is a two-step process. This is non-classical growth, and this is the Gibbs free energy changes in the non-classical system. So sometimes after form in the non-classical growth, after form the nucleation cluster or after form the nucleus will attach together like something like it will attach like this. The attachment is not randomly, it has some orientation. It is not a random attachment, it gives some orientation. So we call it as mesocrystals. So mesocrystals are some crystallographically oriented nanoparticles. You can say it is a mesocrystals. You can see further what is mesocrystals. So now you can understand that classical growth is kind of layer by layer or addition of atom by atom or addition of molecule by molecules. When you cut the single crystals, you can see very clean surface like a kind of apple. So when you cut the apple, the surface is very clean because it is made up of flesh. In the classical growth, it is formed actually addition of atom by atom. So it is very clean. In the case of non-classical growth, whether it is hierarchical material or whether it is mesocrystals or oriented attachment, there are different things. If something happen due to particle attachment, we can say it is non-classical growth, like the pomegranate. If the particles has a particular orientation, if it has a well-defined domain, for example, if you grow some magnetic material, it has some well-defined orientation and well-defined boundaries. So you will get, we can say these are non-classical growth. So if anything happened due to particle attachment, we can say it is non-classical. If anything happened by atom addition, we can say it is classical. So the hierarchical structure actually comes under non-classical growth of crystals. So we can say non-classical growth, it is a kind of a particle attachment. It shows both a single crystalline and a nanocrystalline property because it is mostly in a micron in size. So if nanoparticle is nanometer, bulk material has millimeter in size. Mesocrystals or the hierarchical structure have both, we can say these are intermediate in terms of its size. Yes, the size is in micron. And we can have some space to control the growth because it is a two-step process. In the classical case, after from the supersaturated solution, we can get a nucleus. It is a first step process. The only space you can have to control the crystallization is a supersaturated solution. But here there are dense liquid space, so we can have some extra space to control the crystal growth. These are some advantages in non-classical crystal growth. So mesocrystals, how to define mesocrystals? It is a spatially separated, self-assembled, and crystallographically oriented nanoparticles. You can see there are some aggregation. In the aggregation, it is not a, there is no crystallographic orientation. If you diffract using X-ray, it won't diffract like single crystals. But these mesocrystals, even though it is attachment of particle, when you use X-ray, it will diffract like single crystals. That's why I used the term crystallographically oriented nanoparticles. So mesocrystals are spatially separated. There is a space between basic building unit. So we can see this is a mesocrystals. So this is mesocrystal. There is a space between particles, nanoparticles, and it has some crystallographic orientation. It is not like a randomly attached. We can call it as mesocrystals. The mesocrystal term was first introduced in the year of 2005 by Professor Helmut Koffen from Germany. And we can say the mesocrystals are actually a two-phase system. Like what we saw in the natural mesocrystals, there is a organic and inorganic material, and there is a amorphous and crystalline phase. It is, so we can call it as a two-phase system. The one phase should be crystallographically oriented nanoparticles, and the other phase can be any other entity. In some cases, it may be we can use some organic material, or some amorphous of the same crystalline material can be in between the crystalline particle. So based on this, for example, in the amorphous case, sea urchin spine is the example. The organic layer in between the crystalline unit doesn't occur. So to further explain what is classical and non-classical, if you assume this is non-classical, the right side is non-classical, and this is classical. So here, this is the nucleation cluster. In the classical crystallization, this is the nucleation cluster. Once the nucleation cluster reaches the critical radius, you will get a nucleus. The nucleus will further grow either atom by atom addition or layer by layer growth. You will get a bulk single crystals. So if you cut the crystals or if you break the crystals, the cleavage plane is very clean. It is a classical grown crystals. What is a non-classical growth? So this is the nucleation cluster. Also, there may be a pre-nucleation cluster. We saw it is a tense liquid phase. It is not only in the pre-nucleation cluster, may be different things. For example, sometimes it may be droplet, sometimes it may be complexes, sometimes it may be small clusters. Not only the tense liquid phase, there may be some other things in the pre-nucleation cluster, it may be different. So after the pre-nucleation cluster, it will reach the nucleation cluster. Once the nucleation cluster, you can get the nucleus. The nucleus will attach here in a crystallographic manner to produce mesocrystal. So here, to stabilize the nanoparticles, you can use different additives or different surfactant or different polymers to get a mesocrystals. Based on the stability, it will produce mesocrystals. So for example, if you don't stabilize the nanoparticle, it will produce oriented aggregation. It will produce oriented aggregation. Suppose once the mesocrystal is formed, but still it is not stable, it will fuse to oriented aggregation. If the oriented aggregation is not so stable, again it fuses to single crystals. So there are some possibility. The thing is, we need to stabilize the nanoparticle to get either oriented aggregation or mesocrystal. So comes to this hierarchical structure. After from the nucleation cluster, there may be some, the nucleation cluster will attach together to form a bulk liquid droplet, or we can say it is amorphous phase. After the amorphous phase, it will tense, or some crystals will appear on the surface of the amorphous, and it finally produces hierarchical structure. So this is the pathway for the hierarchical structure. This is the nucleation cluster. The nucleation cluster will attach together to produce amorphous liquid droplet, bulk liquid droplet. After from the bulk liquid droplet, there may be some small nanoparticles, and this nanoparticle attached together to form a hierarchical structure. So what is the difference between mesocrystal and hierarchical structure means? If you diffract hierarchical structure, it won't always produce like a single crystals pattern. It produces the polycrystals. So your diffraction pattern is a kind of ring. But when you diffract the mesocrystals, you will get only spot pattern. Yes, it is a pure single crystals. It is not a, we can say it is a defect-free crystal. It is pure single crystal, but it is made up of nanoparticles. So, so in order to further explain, I'm using the most threatening image of the year, coronavirus. So there are some spikes here. This is the particle. When you attach these two particles, it will produce some space between the particles, or we can say it is a spatially separated. This is the key role for the. This is the key role in the property used to use this property for different applications. And these are some laboratory grown mesocrystals. For example, here, this is a barium titanate where you can see clearly the particle attachment. There's a nanoparticle are attached together. And sometimes people report, for example, in this paper, they have reported it is a superstructure. They didn't mention, they didn't use any mesocrystal word, but they reported as a superstructure because people is not so aware about what is non-classical crystallization, what is mesocrystals. So once they get a hierarchical structure, they use it for different applications. So actually this is mesocrystals. And this is a calcium carbonate, like a nacre is a natural mesocrystal. This is a laboratory grown mesocrystal using calcium carbonate. They use polystyrene sulfonate as a polymers to separate the nanoparticle unit. And this is a natural grown crystals, very laboratory grown crystal where you can see the surface is not very smooth like single crystals. It looks like a unsmooth surface or not smooth surface, or maybe sometime it looks like hierarchical structure, but it always diffract like a single crystal and it only produces spot pattern. And this is the case of organic crystals. This is a DL-alanine. It is an amino acid. The amino acid has a permanent dipole movement to separate the nanoparticle unit. And the people also use some polymers to produce these DL-alanine mesocrystals. This is the mesocrystals of DL-alanine. To further to see what is inside, they used some edging. They dissolved in methanol and reported this SEM image where you can see clearly the attachment of particle. And this is single crystals of DL-alanine. So where you can see clearly what is the difference between mesocrystal and single crystal. This is a pure single crystal. This is mesocrystals. At the same time, it diffract like single crystals. So we call it as mesocrystals. Yeah. So here, this is a single crystals. Even though it is single crystals, the outer surface looks like a not smooth. So people easily come to or decisive. Then they come to understand, come to conclusion that it is kind of mesocrystals. So what they did, they cut the crystal using focused ion beam to see the internal structure. The internal structure is completely single crystals. These are some defect. So this is a completely single crystal. Even though it looks like a mesocrystals, even though it looks like a hierarchical structure, after cutting the crystals, the cross section is completely single crystals. It is not made up of particle attachment. But in this case, this is another organic crystals, ibuprofen, where I use this focused ion beam to cut the crystals. The outer surface looks like mesocrystals, but we don't know what is happening inside. So whether it is made up of attachment of particle or it is made up of atom by atom addition. So in order to confirm, I cut the crystal using focused ion beam where you can clearly see the nanoparticle attachment. So this is one unit. So attachment of particle, we can call it as mesocrystals. There are some difficulty to confirm whether it is mesocrystals or single crystals. People easily comes for a decisive understanding that sometimes they wrongly reported single crystal as mesocrystal or mesocrystal as single crystals. So we need some different technique to confirm whether it is mesocrystal or single crystals. And again, these are some difference between what is a classical and a non-classical approach. Then the classical approach, the nucleation is actually formed by, there is a concentration difference between a solution, concentration difference in the solution, or we can say fluctuation of concentration in the unstable solution produce nucleation. In the case of non-classical approach, there is a reduction in dynamics of particle to produce nucleus. Here, it is a one-step process. Non-classical is a two-step process. Here it is a growth is by ion addition. In the case of molecular crystal, it is molecule by molecule addition. Here it is a particle attachment in non-classical growth. We can say classical approach is a molecular mediated growth. Non-classical approach is a particle mediated growth. The crystal, sometimes it looks like even sometimes single crystal also looks like a unsmooth surface. The outer surface may be not smooth like a single crystals. It is actually happening due to Oswald ripening. I will explain what is Oswald ripening later. Here, it is a kind of oriented attachment, like a crystallographically oriented attachment to explain the further growth. In a classical approach, even at a low supersaturation, we can get a crystals, but for the non-classical approach, we need high supersaturation. So based on the stability, it will produce hierarchical structure, or it will produce mesocrystals, or it will produce oriented attachment. Everything is based on how you are controlling the basic building unit nanoparticles. So here the addition and the primary unit encode the crystal phase. So how the molecules are attaching, how the ions are attaching, define the property. But in the case of non-classical, it is mostly non-classical crystals are anisotropic crystals, because the growth direction will change at any point, because it is a kind of attachment. So the growth will change at any point. So mostly it produces anisotropic nanoparticle. We can produce a different way to produce mesocrystals. For example, here they use some organic matrix. For example, you can use some polymers to separate the primary building unit. Here they use some physical force. Physical force in the sense, for example, some molecules have permanent dipole moment. For example, amino acid, it is a deuterionic ion. You can use as easily, you can easily get a mesocrystal, because the force, opposite force between two molecules separate the nanoparticle unit. So we can use some physical force, inherent physical force to produce mesocrystals. This is kind of epitaxial growth to produce mesocrystal. Here they used some epitaxial growth, means a kind of secondary nucleation. After forming the crystals, at the expenses of the mother crystal, it will produce another crystals. We call it secondary nucleation or epitaxial growth. Here they use some external constraint to produce mesocrystals. This is oriented attachment. They use some phase selective molecule to produce mesocrystals, and this is topotactic or solid phase transformations. So in a different way, we can produce mesocrystals. Mostly the simple technique is we can use some additives to control the particle attachment. At the same time, we need to maintain some high supersaturation to produce mesocrystals. These are iron oxide mesocrystals, where you can see clearly this mesocrystal structure. When we use this particle for X-ray diffraction, this is the SAD pattern, where you can see it is a spot pattern. If it is hierarchical structure, sometime mostly it will produce a ring pattern, but it is a spot pattern. We can say it is mesocrystals. And this is the iron oxide formation pathway. Iron oxide actually is a magnetic material, so you can see a different domain at a different orientation and well-defined boundaries. So after collecting TEM image, after using electron microscope, we can get construct the images collecting at a different angle from -69 to +69. We can construct the image to get a three-dimensional image. This is the tomogram. We call it as electron tomogram. This is the crystalline unit. The green is the another entity to separate the crystalline unit. This is the iron oxide mesocrystals. This is the electron tomogram constructed image. Okay, so what is a oriented attachment in the non-classical crystallization? Sometimes before to see what is oriented attachment, we should know what is a Oswald Ruppning. Oswald Ruppning means after form the supersaturated solution, the nucleus size is not so uniform. Sometimes it may be large or small. Once it cannot reach the critical radius, it will dissolve and attach to the large size particle. You can say it is a Oswald Ruppning. The small particle cannot grow further because it cannot reach critical radius due to surface free energy. So it will dissolve and attach to the large size particle. In another way, we can say the big fish eat small fish to grow further. So we can say it is a Oswald Ruppning. Oriented attachment is similar to Oswald Ruppning, but here, see, this is the two particle. The two particle attached together to produce oriented. We can say it is a oriented attachment. Here there is no lattice mismatch in the oriented attachment. This is the only difference where you can see when you. I'm sorry. I have closed it. Yeah, where you can see in the oriented attachment, there is no lattice mismatch between the two particles. We can say it is a oriented attachment. So this is the difference between oriented attachment and Oswald Ruppning, though the process looks same. So how to see what is happening inside the solution, whether it is oriented attachment or it is mesocrystals, how to confirm it? We can use a liquid cell TEM. TEM normally we use for solid sample. We can also use liquid sample holder to see what is happening in the liquid level or in the supersaturated solution. This is a liquid cell image of oriented attachment. Here, this is one particle, this is another particle. It is not just happening, just attaching two particles. The small particle has to choose some right place to attach with another particle. It will not attach randomly at a particular place. It has to choose some right place to attach with another particle. So the process may happen by, so here it is try to closely contact with another particle, and it assume it is and again it is rotating. It try to contact with this particle. Again it is rotating here to completely attach with this particle, and this particle decide that this place is not so suitable. So again it detach here, and rotate in some other direction to attach with this particle. Then finally it find the right place to attach with this particle in the oriented attachment. Then it attached completely. So the whole process happening within 15 minutes. Within 15 minutes, the attachment process completed. And this is the lattice fringe image of this attachment, where there is no lattice mismatch in the process. And this is they have used a cryogenic TEM to see whether it is mesocrystals or oriented attachment. So this is the oriented attachment of the iron oxide, oriented attachment of iron oxide. This is mesocrystals of iron oxide, where you can see the attachment of particle. So if you keep the solution for a particular day, for example, in this case, they kept the solution for 15 days to get a oriented attachment. So where you can clearly see the particle attachment, this is the mesocrystals. So on the bright spot is a crystalline unit, and the dark spot is a non-crystalline unit. Here it is the water. Water is the non-crystalline unit to produce mesocrystals. If you keep these mesocrystals for particular time, based on the stability, it may fuse to oriented attachment. And if you further kept the solution for some other day, it may fuse to single crystals. Everything is based on the stability. If you need mesocrystals, you need to highly stable the mesocrystals or nanoparticle unit. So though we have some advanced in situ measurement, for example, liquid cell TEM, liquid cell AFM, the mesocrystal research is still immature or unmature, we can say. Still people are using some sophisticated facility to confirm the mesocrystals are oriented attachment. There are some limitation with the liquid cell TEM also. whereas in the liquid cell TM resolution is very high. So we can see only very few building unit to observe the process. In the liquid cell AFM, we can also use AFM to see the mesocrystal orientation, everything. But AFM is mostly good for solid sample. When you use a liquid, maybe we cannot get a high resolution image. And also create-EM, we can use what we can do in the create-EM means we can freeze the solution to get what is happening in the what is happened in the solution. But the crystallization process is very fast. Within 15 seconds, within 15 minutes, it will complete the process. So you need to harvest at a different stage to see whether it is oriented attachment or mesocrystals. So the mesocrystal has a different property. For example, it has increased surface area. Yes, the size is in micron. And there is a uniform voids, but in the internal structure, it is actually intermediate in terms of its size. So you can get both the single crystal and the nanoparticle property. And it has some reactive facet because the outer surface is not smooth. So it has a reactive facet. By using this property, we can use these mesocrystals for a different application, like a hierarchical structure material. We can use this mesocrystal as an electrode in battery and a supercapacitor. We can use a mesocrystal as a photocatalyst. We can use mesocrystal for high mechanical strength cement. For example, the Portland cement, it has maybe you may hear that a quick cement. Quick cement mean you have to increase particular ingredient. For example, the Portland cement has a dicalcium silicate and a tricalcium silicate. Based on the stoichiometry ratio, whether it will be quick cement or normal cement. So in the building material, calcium silicate hydrate is the role to strengthen the concrete. If we prepare that calcium silicate hydrate in terms of mesocrystals, in the form of mesocrystals, we can increase the concrete strength. And mesocrystals, the metal ionic framework can be also prepared as mesocrystals. What I'm working here is that I'm using pharmaceutical solids in the form of mesocrystals to enhance the dissolution of drug. So mesocrystal is a photocatalyst. Already, for example, already they have enhanced the efficiencies, for example, 10 times higher than normal titanium dioxide. If you prepare titanium dioxide in the form of mesocrystal, the efficiency has increased 10 times. So we can also use mesocrystals as an electrode. We can also use electrode, titanium as an electrode in lithium-ion battery. Lithium orthosilicate has been used as cathode in lithium-ion battery. And if you use a mesocrystal, if you use an electrode in the form of mesocrystals, the lifetime of the battery is very high. For example, excellent cycling performance, large reversible charge discharge capacity has enhanced when you use the electrode in the form of mesocrystals. And the tin oxide they have used as mesocrystal to detect, to sense. It has a different oxygen vacancy. So it is when you prepare this material as a mesocrystals, the sensing has increased. For example, high response and the sensing response is 50 parts per billion for nitrous oxide. So copper oxide can be used as mesocrystal to sense ethanol. Zinc oxide, copper oxide can be used as for hydrogen sulfide. And cobalt oxide can be used as mesocrystal to sense formaldehyde and ethanol. So we can use sensor, and we can also use mesocrystal electrode as the electrode in a battery and a supercapacitor. So here I'm using mesocrystal strategy to enhance the dissolution of the drug. The major issues in pharmaceutical industry is that about 90% of drugs in pipeline or 90% of new drug has solubility issues. Even 40% of drug in the medical or 40% of the drug, the market approval has a solubility issues. Sometimes that's why a doctor asks you to take some medicine in a warm water. If you take medicine in warm water, it will easily dissolve and quickly cure the disease. So this is the idea. I am preparing pharmaceutical drug or a drug molecule in the form of mesocrystal to enhance the solubility or enhance the dissolution. So I got funding from European Union to conduct this research at Alta University. So why organic mesocrystals compared to inorganic material? Organic material has some advantages. Like an inorganic material, the molecule don't have any permanent dipole moment. But in the case of organic crystal, the molecule has permanent dipole moment, for example, amino acids, and it has a hydrophilic and hydrophobic interactions. Using these interactions or using this physical force, I can separate easily the basic building unit. This is another advantage. Low lattice energy is another advantage in mesocrystals. In the case of inorganic material, the lattice energy is very high. The lattice energy is very high, it will easily produce single crystals, not mesocrystals or oriented attachment if the lattice energy is very low. So this is another advantage in organic mesocrystals. And naturally, it has a wide and high surface area. By using this property, I can use this strategy to enhance the dissolution of poor aqua-soluble drug. So to conclude my talk, the mesocrystal is a two-phase system, and it is an intermediate to have the properties of bulk and nanoparticle because the size is in micron. We can have some extra space to manipulate the nanoparticle to design particular material using this mesocrystal strategy. The internal external features, for example, voids or amorphous phase, highly faceted crystals, we can use this property to enhance the material property. And another thing is we can also prepare the existing functional material in the form of mesocrystal to tune the property. The formation mechanism is still needed to understand because we need some high resolution and different technique to confirm whether it is mesocrystals are oriented attachment. This is the still people are working on using a different technique. And this, though it has some disadvantage to confirm whether it is mesocrystal and single crystals, using some internal and external features, we can use mesocrystals for different applications like hierarchical material. And I would like to acknowledge different funding agency who supported me at different stages of my research career. I got funding from European Union, and I got funding from China Postdoc Council to carry out my research work at Shandong University, China. I got some more funding from Finland to carry out part of my PhD research work in Lappeenranta University of Technology in Finland. I got funding from ACRP to attend a conference, and also got funding during my PhD from DRDO. And thank you so much for your kind attention. Yeah.
Thank you. Thank you very much, Dr. Rajbobji. Very inspiring and informative talk on the classical and non-classical growth, okay? Especially the origin of mesocrystal and its applications. Thank you very much. Okay?
Thank you, Saravanan, for co-hosting this session. Yeah.
Thank you. Thank you. Now the session is open to the participants. Participants, if you have any questions or discussions with Dr. Rajbobji, please welcome. Okay. If you have any questions, please you can use the raise hand option, and you can discuss with Dr. Rajbobji. Any queries from the participants? Audience, participants.
You can freely ask if you have any question, and I will happy to answer and try to answer in my best.
Sir, I'm audible?
Yes.
Yes,
sir.
Robert, yeah, you can ask your question. Yeah.
Sir, if anisotropic means the material depends on the direction.
Yes.
In meso, here also it's same, sir.
Yes, actually, in the mesocrystal formation, it is a kind of particle attachment. In the case of classical crystals, what is happening in the supersaturated solution, you cannot change between the bulk crystal process and nucleation. So you cannot, you don't have any extra space to control the classical things. But in the case of non-classical crystallization, it is a kind of attachment. The attachment will change at any point to grow in a particular direction or a different direction. For example, at a particular plane, the arrangement is at a particular orientation. In another plane, it may be different. So you can get mostly anisotropic nanoparticle in the non-classical crystallization. If it is anisotropic at a different plane, you can get a different property or different application. Yeah. Mostly it produces anisotropic. Yeah.
Yeah. Any other questions from the participants?
Sir,
Yeah. Yeah, you can ask.
sir, if anisotropic mesocrystal will elongate along the direction of magnetic field, sir?
It is based on how you are controlling. For example, if you use some polymers, it will produce particular kind of things. If you use other polymers to stabilize the nanoparticle, in which way you are controlling or what kind of additives you are using to control the alignment. Everything is based on the experimental parameters. You have to adjust different parameters to enhance the or further tune the properties at a particular direction. Or yeah, everything is same. The thing is we need to use some external entity to control the particle attachment. Otherwise, it will produce a bulk single crystals. Yeah.
Thank you, sir.
Yeah.
So, few questions from the chat box. I will read out. Yeah.
Yeah, please.
This is from Neha Prakash. She asked that why the crystal radius is negative, and what is its practical significance? Why the crystal radius is negative? And what
maybe she is asking whether it is a positive king side, negative king side, because there is no negative radius or positive radius. I think so. Yeah, king side. In the classical crystallization process, there may be positive king side or negative king side. The king side means it is the position or it is the location where the next molecule will come and sit there. Either it may sit in a positive or it may be negative. The positive and the negative is based on the Gibbs free energy of the system. What is the surface energy? Everything is based on the internal system, Gibbs free energy of the internal system. Yeah.
One more question is Sudha, G. Sudha. She noted your application slide. From that, she is asking why titanium oxide in rutile phase is more stable compared to anatase.
Titanium dioxide is more stable compared to anatase.
In rutile phase is more stable compared to anatase.
Actually, I am not working in a titanium dioxide. I think I remember that titanium dioxide has a different, it is a polymorphs. It is a rutile, anatase, something. So her question is what? Why it is stable?
Yeah, in rutile phase is more stable compared to anatase.
It is actually polymorphism means a same compound prepared or formed in a different crystal system. For example, even though if it is a titanium dioxide, one form may be one system, another form may be another system. So if the crystal system changing means crystal property will be different, even though the crystal looks like same. For example, sometime in the same chemical entity, if you use the same chemical entity, for example, titanium dioxide, it will produce a green color in a particular form. Another titanium dioxide may be a red color. Because the crystal system is different. Crystal system is different means properties are different. Properties different mean stability may be different. So it is based on the crystal system. Titanium dioxide is a polymorphism. It will produce a different system. It has three forms. So when it has three forms, the properties are different. That's why rutile may be more stable than anatase, I guess. Yeah. It is based on the crystal system. Yeah. It is actually polymorphism.
Another question is crystallization depend on agitation?
Crystallization
depend on agitation.
Yeah, agitation of the solution. How, like at the initial stage, how the crystals forms. It is based on the concentration, fluctuation in the concentration or agitation. Yeah.
One more question is there any correlation between the bond strength of a growing crystal and the crystal growth rate? Is there any correlation between the bond strength of a growing crystal and the crystal growth rate?
There are, it is mostly depend on the crystal growth rate is based on the parameters, different parameters. As far as I know, for example, if you use a high supersaturation, or if you use a low supersaturation, or your solution has high viscous or low viscous, everything is based on the parameters. I don't think, even for example, the same molecules with the bond length or bond strength is the molecular property. Even for the same molecular property, or even for the same molecules, if you use a different parameters, your growth speed or growth rate will be different. So it is not depends on bond strength. It is based on what parameters are you using to grow the crystals. Yeah. As far as I know.
Two more questions. Yeah. Two
Yes,
more
yes,
questions
please.
there.
Yes.
This is from liquid cell temp, regarding liquid cell temp. What
Mm.
are the conditions for the particle to rotate and find a place for attachment?
It is actually self-assembled process. You can't do anything. It is a self-assembled process. It will assemble based on the interaction things like interaction forces. You can. It is a self-assembled process. You can't do anything in the liquid cell TEM. Yeah, it is a self-assembled process.
One more question is, can we think of mesocrystal thin films? What could be the most suitable synthesis process for it?
Actually, I don't have any idea for the thin film. Whether they have even, I haven't read any papers related to thin film mesocrystals. Maybe if anything, I will let you know, or you can contact me through email. I don't have any idea thin film mesocrystals. Yeah. We are using bulk single crystals. Yeah.
Any other questions from the audience? I think, yeah, that's it. Yeah, okay. Thank you, Rajabudi. Thank you for the informative talk on this mesocrystals, which is a building block for all sides of research. Thank you very much for joining with us. Thank you very much.
Thank you, Sarvana, and thank you for the organizing members, conveners.
Thank you, sir.
Yeah.
Thank you very much, sir. It was really an informative speech. Thank you, sir.
Thank you, madam. Thank you.
So we'll move on to the next session. Due to unavoidable situation, Dr. Sarochan Yuria from Thailand, she cannot join with us. We have Dr. Somnath Roy, Associate Professor, Department of Physics from Indian Institute of Technology, Chennai. And he has accepted our invitation in a short time. So I welcome you, sir. Thank you, sir, for accepting our invitation. Thank you very much, sir.
Thank you very much.
Now I request Dr. M. Saravanan, Department of Physics, to introduce our resource person, Dr. Somnath Roy, sir. Saravanan, sir?
Yes. Yeah, very good afternoon to all. It gives me pleasure to introduce Dr. Somnath C. Roy, okay, from IIT Madras. So, Dr. Somnath C. Roy completed his BSc and MSc in physics from Banaras Indian University, Varanasi, and completed his PhD from IIT Delhi by the year 2005. After that, he joined as a lecturer in the Amity University, Noida for a short-term period, and then he joined the Material Research Institute at Pennsylvania State University, USA by the year 2006 as a postdoctoral researcher. In 2011, he moved to IIT Madras as an assistant professor in the Department of Physics and became associate professor in 2015. And with this, during the past 11 years at IIT Madras, he has been actively involved in the growth and study of one-dimensional nanostructures for solar energy and gas sensing applications. And Dr. Somnath C. Roy so far guided 6 PhD students, and at present, Dr. Roy's group, called as the Environmental Nanotechnology Lab, is comprising of 8 PhD students and 2 postdoctoral fellows. Okay? He has received several funding from reputed funding agencies such as DST, DRDO, CSIR, ONGC, MISAN, and SERP. And at present, he has a total of 58 publications, and H index is 15. Okay? He had been selected for the Bhaskara Advanced Solar Energy Fellowship and also the Shastri Indo-Canadian Institute Faculty Travel and Internationalization Award. Okay? So with this introduction, now I request Dr. Somnath C. Roy to present his research model. I welcome you, sir. Sir,
thank you.
Now we can start. Thank you very much, sir. Thank you.
Is it visible?
Yeah, yes, sir. It's visible. Yeah.
Yes, sir. Yes, sir.
Yeah. You make it as a full screen.
Actually, I'm not putting it in the slide mode because my laptop has some problem. Slide mode slides do not change.
Yeah,
so
okay.
I'm just putting it in the normal mode. But I think it is clearly visible, right?
Yeah, yes, sir.
Yeah.
Okay. So good afternoon to all. It's really a pleasure to be able to talk at this virtual international conference. So the title of the talk is A Beautiful World of One-Dimensional Metal Oxide Nano and Heterostructures. I'm from the Department of Physics, IIT Madras. Let me tell you, give you a disclaimer right at the beginning of the talk. It is a well-known proverb in English that beauty lies in the eyes of the beholder. So as a presenter, my work for me is always beautiful. Unless I feel my work is beautiful, I cannot enjoy my work. My students cannot enjoy my work, our work. So the things that I'm going to share, I'm going to show to you, all may not look beautiful to all, but feel free to object, obstruct, raise questions, debate, discuss, whatever way. And even after this presentation, I'm always available. Those who are from nearby Chennai or in the city, when the situation gets stabilized, can come and visit our lab. So all these few introductory things, let's start. So outline of the presentation. I'll just give a brief background, what motivates us to work in the nano. TiO2 graphene oxide nanostructured composite. Then we will go to copper oxide nanoflex and cuprous cupric oxide heterostructures. Vertically oriented bismuth ferrite nanorod, and we have done some. So recently we are moving to some more fundamental work from materials engineering to nanoscale physics, and we have tried to look into more detail or in depth about one single nanostructure, future outlook and acknowledgement. So can you see the third slide, focus and theme of research? Sarvanan sir, can you see?
Yeah, it's visible. Yeah.
Okay, fine. Thank you. Yeah, that I wanted to confirm. Okay, so as I said, one-dimensional nanostructures. One thing you will see during my presentation is that most of the work that I present here, we'll see the nanostructures grown directly from substrate. Okay, partly that it comes from my background of thin film. I was trained as a thin film person in IIT Delhi during 1999 to 2004. So we used to grow thin film all the day and night, 7/24, 365. So anything that can be grown from a substrate always fascinates me, always comes naturally to my mind. And if you come and say that, sir, can you work with some powder? I can of course work with powders, bulk materials. But whenever you give me a substrate and say, do something from here, it's always very natural. It's like I call myself that, I'm a real estate guy in the nano world. So what real estate means, these people actually construct buildings on open ground, right? So that's why my ground is substrate and I construct buildings in the form of nanostructures. And the second thing is that we were interested in photoelectrochemical water splitting and gas sensing, again, partly because of my background, but we are slowly actually going to several applications in collaboration mode. So the first thing is photoelectrochemical water splitting. It was given, the idea was floated in 1972, that is even before I was born. The idea was that if you have water, of course, it's not very pure water, it's pH controlled water. And then if you have one electrochemical system, one side you have a cathode, you can take a standard cathode like a platinum. On the other side, an anode. This anode has to be a semiconducting oxide or a semiconductor, let's say. And in a way that if the anode, you shine light, if the anode can absorb light, then it actually creates electron hole pairs. And those electron hole pairs actually carry out redox reactions with water. And the result is that you get water is split into hydrogen and oxygen, where you can use hydrogen for fuel cell, let's say, or anything you want to produce electricity. For example, in fuel cell, if you do, then you again produce water, and that water goes back. So in a way, it's a beautiful self-sustaining energy cycle driven by sunlight and water. Both are available. And it's really, when the concept was floated, it really had the power to, I mean, everybody thought it will change the world. Of course, we now know that there are a lot of technological hurdles, primarily coming from the extremely low efficiency of the process, and they're working. Nevertheless, although commercially this thing has never been implemented in whole, but the concept has actually proven useful for many things from there: solar cells, Dyson-based solar cells, and many other things. But on the other hand, even if the concept has not been commercially successful, this concept actually results in thousands of PhD theses all around the world every year, because it's so challenging. Even 1% increase can get someone a paper in Nature. It's like that. And then academic research, you always work with the problems that may not have immediate technological relevance, but then there is a fundamental scientific problem that you are trying to solve. So the whole thing is based on the concept of photocatalysis. So this concept of photocatalysis is simply that you have a material that can absorb sunlight, produce electron hole pairs. As you can see here, on the right side, you have valence band and conduction band. And then when you shine light on a material, electrons go from valence band to the conduction band. Now, the beauty of this process is, as those blue mentioned in blue, that reaction mechanisms will show, you have both role played by both the electron and hole. Electron will go to conduction band. They will reduce something which is in the vicinity. Hole will be there in the valence band. Hole can also oxidize water. In fact, hole starts oxidizing the water. Now, if you say that how hole actually oxidize, hole is a vacancy, how hole oxidize. So if you just give it a thought, that a material giving out holes is simply as that, suppose some material is in touch with a semiconductor, and we say this semiconductor is giving out holes. That means simply the material which is in touch with this semiconductor, that material is giving electron back to, or electron into the semiconductor. So it's always a bit confusing concept, particularly for the students in the lower classes who didn't have a solid state physics background to understand hole means nothing. Hole is vacancy. How hole can do so many things. So its hole is only the concept. Finally, it's the electron everywhere. Whether it's a valence band, when it's a valence band, we say hole is coming out of the valence band, means is the electron going into the valence band, if the energy levels are properly aligned. And then there is conduction band. You have electron, and the electron, if the electron finds another energy level of a material in vicinity which is suitable, then electron can transfer. It's just like that. So the entire concept rests on you have light. The light shines, produces electron hole pairs. So So this system, as you see in the bottom, you have water and you have an electrolytic cell. I have shown here a reference electrode. So three cell electrolyzer. Not always it is required, of course. That has its own advantage. I'm not a hardcore electrochemist, so I'll not go into the discussion of this reference electrode at all. Excuse me. But so essentially, if it's an N-type material, then we have an anode that is in the form of that semiconductor that we are talking about. I'm going to talk about how we actually work around this semiconductor to develop the nanostructures for this semiconductor. So what are the desired properties for the semiconductor? To be able to split water. Suitable band gap for visible light absorption. As you see, of course, you want the maximum light that is available with the in the solar spectra to be absorbed. Now, you know the solar spectra has about 4 to 5% UV, about 45% of visible, and about 50 something about IR. Generally, of course, you want visible and UV to be active. We don't talk much about IR absorption because IR also has a little long-term problem that heating in the sample can degrade the material. Of course, if you can absorb IR without any degradation of the sample, that is the best. That happens in silicon. Why? That is why silicon has 1.1 electron volt band gap. It actually absorbs the entire spectrum. So that is so generally we want visible light absorption. Visible light absorption means the band gap of your material should be around up to 2.1 or 2 electron volt. Fast charge separation and conduction, low loss. You want when the electron hole pairs are created across this conduction and valence band, you want them to be separated pretty soon. If you don't separate them, they come back and they will actually essentially recombines, and that is a huge loss. So you want them to be separated. Appropriate valence and conduction band position. This is in fact the most challenging part of photocatalysis in general. That even if I have materials with suitable band gap, the problem comes in two ways. Either the material is not stable in water, that is the problem comes, or let's say I am trying to run a photocatalysis process where my electron in the conduction band, the hole in valence band. Now the electron requires a certain energy to initiate a reduction process. The hole requires a certain energy to initiate the oxidation process. That's fine. Now let's say I have this gap is band gap. This gap is also suitable visible light absorbing. Now let's say I have a material where this gap is good, but this is somewhere here, this is somewhere down. I mean, these reference levels I'm talking in terms of electrochemical energy, or let's say vacuum energy. So I need to have this conduction band at a certain position, this valence band at a certain position, plus this gap also. So all these conditions need to be fulfilled, which is really challenging for a single material. That's why so much of heterostructures. So non-corrosive, non-toxic stability under illumination and humidity, because you are talking about water splitting. So the water splitting simply means that your material has to be dipped in water, always immersed in water. Obviously, the material has to be stable. So that's why we talk about oxide materials. Higher surface to volume ratio for a faster reaction. So we want a nanostructure which has a higher surface to volume ratio. If you have a higher surface to volume ratio, what happens? That lot of its surface is in contact with water or your reaction medium. So the electron and holes can easily interact with the medium around. If that is not nanostructure, if the surface area is not high, the electron and holes will recombine within the material. So tailoring a material at the nanoscale with respect to both microstructure and electronic property hold the key to success. So here we come to one-dimensional nanostructure. So if you say one-dimensional nanostructures, we are trying to mean here nanowire, nanorod, nanotube type of things, which obviously like any other nanomaterial have a high surface area, easy charge separation, regular porosity, orientation, and aligned morphology. So here two things I would like you to notice here. Once I say one-dimensional nanostructures, let's consider this pen. Okay, let's say it's a thin thing, one-dimensional thing, okay, just so that the electrons can move only from one side to the other. The electrons cannot move on the, let's say, XY direction, only, let's say, Z direction. And the another point is that we are interested to grow them from a substrate, as I said right in the first slide, that if you all grow them vertically aligned, one after other like this, all are aligned together, then it's much easy to control the morphology and to much easy to, predict the properties compared to a randomly oriented nanoparticle powder, or let's say carbon nanotubes lying, not carbon nanotube, those who work on carbon nanotube may feel offended. So let's say some nanostructure randomly lying on the substrate, horizontally lined on the substrate. So compared to that, if I have this aligned nanostructure like bamboo sticks all grown from ground, it is a much easier morphology. That's why we said nanostructure directly grown on a substrate, vertical orientation. Again, titanium dioxide, I will first come to titanium dioxide. Titanium dioxide is, in photocatalysis, it is what is, silicon for microelectronics. Whatever you say, still we are in the silicon electronics, silicon world, because of there is so much advantage of silicon. Similarly, even in photocatalysis or thing, titanium dioxide, one of the main reasons, having titanium dioxide, you may not, those who are not from the field may not realize that probably you are now surrounded by titanium dioxide somewhere or other. Where we have these paints in our rooms, even my room, this paint, wall paint, white pigment that has titanium dioxide. We use this talcum powder in the summer. Chennai, summer has already come. So this talcum powder has titanium dioxide, zinc oxide. Okay, the sunscreen lotion, that is almost fully titanium dioxide or its composite. Why? What is the role of sunscreen lotion? It actually needs to absorb the UV light, right? So TiO2 absorb UV light, 3.2 electron volt. So one of the best things. But why? Why you say, sir, why we apply TiO2 at all? TiO2 or zinc oxide coatings? Because even if they enter a little bit in the skin, when you apply a powder or a cream, certainly is going into the skin up to some extent. Okay, very small part. Doesn't create any harm because it's biocompatible. So that is the most important advantage of having titanium dioxide is the biocompatibility, low toxicity, in spite of having a narrow band gap and wide band gap which can absorb only a narrow part of the solar spectrum. Still, majority of research work is on TiO2 related thing. Like in the last seminar itself, the last talk itself, the speaker talked about TiO2 based work, right? So we are working on these nanotubes. As you know, the nanotubes have the additional advantage of having outer surface as well as inner surface. So how do we make these nanotubes? These nanotubes are one of the most simple way to make. All you need is a beaker where we have some acidic electrolyte. Typically, we take, as you can see here, I haven't mentioned about the electrolyte particularly, but we mix, let's say, potassium chloride, ammonium chloride. You can also take, HF. HF is a very fast agent, but HF is extremely dangerous and it doesn't produce much longer nanotube. And we have this, any solvent we take. We apply a constant voltage. So yeah, so most importantly, we have the titanium anode. Since we are going to make titanium oxide nanotube, we have this titanium foil is our starting point. If you do not have titanium foil, what we do for other applications, we deposit titanium thin film on glass or plastic and to get a titanium film, and then we anodize it. So the titanium works as an anode, a platinum as a cathode, the electrolyte, and all you need is a DC power. So with this, with the DC power supply, you apply a constant voltage, and then you get about 30 minutes. So this slide, essentially tells you there is a wide variety of process within anodization, different electrolytes, different things that you can do to get a very nice TiO2 nano. So as you can see here, these are the TiO2 nanotubes fabricated in our laboratory. In fact, almost every day somebody or other makes this nanotube. Basically here, probably at least I will convince some of the 70 attendees, as I can see now, 70 participants, at least probably 7 of 70, 10%, if it's 10% good enough, will say, yes, sir, it is beautiful. So that is the thing I call them, yes, the beautiful world of 1D nanostructure. So you can prepare them in different diameters, different length. You can length go up to 50 micron or more. You can, as you can see, the bottom one, conical, compact, separated nanotubes of different kinds that you can prepare. Of course, this is our work we are showing. Even if you search TiO2 nanotube related work in internet, you will see a lot of innovations people have done. People have taken a doped TiO2 nanotube. People have taken titanium alloy with other metals so that the nanotubes are grown. Let's say titanium vanadium, titanium aluminum nanotube, like that it has grown. There are different, I'm not talking about those work here, primarily our work, but it's really, and one of the most important thing I say, I love about working on TiO2 nanotubes particularly, it can be done in extremely simple manner. You do not need very sophisticated experimental techniques and other things. All you need is a beaker, is a DC power supply, and a platinum piece. That's all, of course, titanium is. So the first part is TiO2 graphene. Okay, excuse me, Savanan sir, how much time I have? Can you please tell me?
Yeah, you can still have 20 more minutes.
20 more minutes. Okay.
Yeah,
I will accelerate a little bit.
Yeah,
so,
Okay.
No, I go typically slow in the first section to put the things into perspective so that everyone is on the page, and then we can. So then TiO2 graphene. Okay, the TiO2 graphene. Now, why TiO2 graphene has two reasons. One reason is technical. Other reason is personal. Okay. Don't think personal means something related to my family. Nothing. But I'm going to explain. So technical reason is that TiO2 has a wide bandgap oxide, 3.2 electron volt, and so it can absorb only UV light. Even with the UV light, if it can absorb all light and can all UV, and it can produce electron hole pairs out of all UV light, still it is good. But the point is that it has a lot of recombination. So as soon as electron hole pairs are produced, TiO2 has very favorable layer of the electrons immediately jump back to the hole and they recombine. So when graphene was discovered in 2004-2005, immediately in 2008, that time I was still doing my postdoc in Penn State, a paper came which shows that TiO2 graphene composite, if you have graphene layers intimately wrapping TiO2, then the graphene can take out electrons very quickly. Okay. So when I came here in IIT Chennai, when I came in 2010, and so that year itself it got Nobel Prize, graphene got Nobel Prize. And I thought, oh, wow, I am working on TiO2, graphene got Nobel Prize. There are 1 or 2 papers on TiO2 graphene. Probably it's a very good opportunity to get some funding. If I quickly, so eventually 3 of my proposals out of 10 proposals, 3 of my proposals are on
Dr. Veena, ma'am. Dr. Veena, ma'am.
Sir? Somnath, sir?
Yeah, his audio is not.
Somnath, sir?
Sir?
I think he had network.
Yeah, he had network.
Yeah, yes.
1 minute, sir. 1 minute. Sir, you can continue, sir.
Sir, you can continue.
Yeah, continue.
I think I got disconnected.
No.
Yeah, yes. No problem.
Sir, you can share the slides, sir.
Can you see that now?
Yes, sir.
Yes, yeah, it's fine. Yeah.
Okay, I'm sorry, I didn't realize when I got disconnected.
No problem, sir.
Okay. So then the TiO2 nanotubes, when we looked up at the literature, we found that there are a few papers in 2012, 2014 around TiO2 on TiO2 graphene. But all of them had a problem of they had taken these compact nanotubes where graphene cannot go to the side of the nanotube, right? There, as you can see on this slide, graphene layers are only on the top of the nanotube. Okay. So that was our first challenge. We encountered this challenge. I will come now. I'll start skipping some slides. Standard practice when I'm running short of time. So the first innovation we did was we carefully crafted our anodization process, where we made the electrolyte in a way that the electrolyte had a little lower surface tension forces. So the nanotubes which were fabricated, as you can see in the top one, were separated. So there are plenty of space around the nanotube for the graphene to be, going around. So as you can see, the bottom two, then we ran the graphene deposition. So the graphene deposition we did with, I'll just go back to the slide. There were two techniques by which we tried graphene deposition. One was photochemical deposition, one was electrochemical deposition. So when we ran one of the techniques, I'm not going to which one and all, but then what we found this beautiful wrapping of graphene layers around the TiO2. As you can see, the lower two slides, lower two pictures. And it was just like a gift wrapping. You buy a gift, you wrap it up with a gift paper, or you have the luggage in airport, they wrap it up with cellophane, something like that, as you can see. So this was really a very strong, I call it a remarkable achievement in the sense that we found an increase in the photocurrent, as you can see here, under sunlight, which actually indicated that we are able to harness more sunlight with using the graphene wrapped TiO2 nanotube. So we did the impedance measurements, which showed that the charge transfer resistance across the semiconductor electrolyte interface. Electrolyte is the water, the pH control water, in fact, actually reduced when we have this, as you can see. But here I should really mention one thing about that. This is not only graphene. This was technically graphene oxide. Since we are taking graphene oxide, means functionalized graphene commercially, we were buying from some sources. We could never get pure graphene across around TiO2. Whatever we do, there was some oxygen functional too. Later on, we realized that that's not a problem. Even if we wanted to have pure graphene, then since there is oxygen in our TiO2, that oxygen will anyway be attached to graphene. So that case, what we call as the graphene oxide wrapped TiO2 nanotube. Then we did a couple of other studies where we found out in detail the charge density calculations, the resistance calculations, all that we did the efficiency calculations, and we found that the graphene oxide wrapped TiO2 nanotubes actually help in enhancing the photoelectrochemical efficiency of the process. One of the work that we did actually around 2018-19, that time we didn't have facilities, so this work was done in collaboration with CSIR IIP Dehradun, Dr. Sumanlata Jain's group. That we also tried to check photocatalytic CO2 reduction with the graphene oxide wrapped nanotube, and of course we found some increment in that initial increment, and we are still pursuing this work. Now we have facilities here in my lab at IIT Madras, where we are active. Now I will come to copper oxide. Now again, copper oxide is a very well-known material. Nothing to introduce about copper oxide. So the point is that the copper oxide, there are two phases of copper oxide. One is CuO, one is Cu2O. Okay, cupric oxide and cuprous oxide, two stable phases. Out of that, CuO is more stable than Cu2O. We wanted to do some work on copper oxide, but my student, this is the work of my third student, who actually pointed out something, who actually found out something, that as if you take copper oxide as such, as a single crystal in bulk material, you find very pure copper oxide. But if you want to go to copper oxide nanostructures, for example, the nanostructures are shown here. nanoneedle, nanoflex kind of thing. Then you always have this challenge of having CO, CO2 mix phase, and which actually resulted in lower than expected photocurrent value. So what is this photocurrent? That when we are measuring current under light irradiation. So that is our photocurrent. Okay. So in this work, what he did was actually he did some very carefully crafted hydrothermal treatments, followed by what is called a rapid thermal annealing. With that rapid thermal annealing, and that rapid thermal annealing he ran for only 10 seconds. 10 seconds, yes, that is only 10 seconds. That rapid thermal annealing. With that rapid thermal annealing, what he was able to do is that he got 4.6 milliampere per centimeter square current, which is a pure single crystal copper oxide nanoflake. Means whatever you see here in this slide, each of these needle type of thing are actually one single crystal of copper oxide and pure copper oxide. So with that, again, we did photoelectrochemical measurements. We did all sorts of measurements. We did Mott Schottky. We found out this. So these things I'm not talking in detail here because it will take time. But only the most interesting things I'm actually highlighting here. Now I will come to the next more interesting part of it. Okay, we did not like having Cu2O cuprous oxide phase, impurity phase inside CO. When I say that, I mean, suppose you have a material which is only CO. Inside the material, some random particles of CO2O, that we don't like. But then there is also a concept of heterojunction. Heterojunction means we found from the literature that if you have, like in the lower part, as you can see here, the lower right, if you have CO2O, CO aligned side by side or top, bottom, like whatever way, not randomly, but one after other, then the conduction band and valence bands actually align in such a beautiful way that you have electron and hole travel to the opposite direction. Means if you have electron in one and hole in, so electron will quickly go to the one face and hole will go to the other face. So this way, this kind of CO2 heterojunction leads to a natural separation of electron hole pairs. Mind it, here we are not talking about only one component. Here the both, it is called the heterostructure. So both components are together. So we thought, since we had made this nanostructure, how to make the heterostructure. So I will quickly come here in this slide. As you can see here, what we did was, here we first started with Cu2O. Cu2O starting, the reason of starting with Cu2O is we did not want a complete oxidation of the nanowire that we are preparing. So when we have an incomplete oxidation, first we get Cu2O. Then in the second phase of treatment, we treated that Cu2O nanowires. As you can see here, these Cu2O nanowires are in the middle. It's like the stem of a tree with another step of hydrothermal process. And we found that beautifully, let's say this is my Cu2O, and CuO actually grows, a CuO flex actually grows perpendicular to the Cu2. As you can see here, the lower TM structure, one is this Cu2O, and then the CuO grows like this, like it's a stem and a branch of tree, as you can see the bottom. Frankly speaking, we still do not know how exactly it is happening. We have given some empirical models, and of course, the referee liked it. We are lucky, so our paper got accepted. And we are working with some crystallographers now and trying to run some DFT molecular dynamic simulations to understand why it grows perpendicular. But then there is some basic crystallographic crystal growth concept which actually tells us that if there is a selective site on, let's say, Cu2O, then the material is accumulated, the first material is grown there, and then the surface energy dictates that it will just grow. Like as this main one has grown single dimension, unidirectional, so this perpendicular also it grows single dimension. So that's how what I call CuO, Cu2O, nanowire nanoflake heterojunction, and with that we got 1.9 milliampere per centimeter square. Now, if you remember 2 slides back, I boasted about having 4.8 milliampere only from CuO. Then you will ask me, sir, what's so big deal about 1.9 milliampere, just less than half? The point is that even CO2 heterostructure, I have already explained what is the advantage of CO2 heterostructure. So these CO2 heterostructures, no one has had achieved nanoform heterostructure almost 2 milliampere current. So the advantage, as I already said, is that you have the electron hole pair recombination, which is minimized in this case. Okay, so that is one of the recent achievements from our group, and of course I will skip that. I'll again skip this also. These are the things. I'll come to the third interesting work from our group. Many of the material scientists here will know the importance of bismuth ferrite. Bismuth ferrite is a well-known multiferroid compound. It has both ferroelectricity and ferromagnetism. But the point is that this is my 5th student's work. So she found out from literature that bismuth ferrite has been prepared in many forms: thin films, single crystal, polycrystalline powder. But no one had actually succeeded in preparing bismuth ferrite in nanorod form. There was, of course, a paper not so far from either, I think, Coimbatore or Madurai. I think Coimbatore. They had prepared it, but their nanorods were extremely short, very short. And there are another group who had prepared using template assisted. We thought of one innovation. We were earlier in my postdoc, I was working on iron oxide nanorods. Iron oxide nanorod we prepare in a simple, much simpler than electrochemical anodization. We prepare it with just a chemical bar deposition. You have iron chloride solution, you put some conductive glass inside, you keep it at 95 degree, mind it, 95 degree. You do not let it boil, the water mixer, 95. And then this nanorods grows from the FeO substrate. Okay. Now, I left it at that point, FeOH nanorod. We sputtered bismuth. I'm going over quickly. We sputtered bismuth. We ran a very carefully programmed annealing, and a resultant is that what we got is the bismuth ferrite nanorod. So as you can see the top view and the cross-sectional view, first we have FeOH nanorod, we put bismuth, then after bismuth we anneal it again. As you can see the top view bismuth. But there are two issues here. My next student is working now to resolve it, that the bismuth ferrite, as you can see in this screen, that the nanorods are there, the XRD. There are two issues. One, we still have some secondary phase of bismuth, that is there, BiFe509 phase. And then the nanorods are still not very long. We could have nanorods around 1.5 micron only. Unlike the TiO2 nanotubes we had around 5-6 micron, we are trying to get this. So we checked for piezoelectricity. In fact, as the CU, the lower one, what I call as the beautiful butterfly, again, which actually confirmed the bismuth ferrite was there. Of course, XRD also confirmed, but XRD shows mixed phase. This actually 100% confirmed that we have piezoelectricity or ferroelectricity in the material, so which is a multiferroid compound. Then again, we ran magnetism. Of course, magnetic values, the susceptibility values, magnetization values are extremely small because of the presence of the mixed phase, as also because of the is extremely short. But then this was the first report where even it's a shorter, it was much longer than the previous report. But even if it is a shorter, it was the first report of freestanding, vertically oriented bismuth ferrite nanorod prepared without any template assistance. So you will see a lot of work on template assisted nanostructure. No template was used. Of course, you can say that we had a two-step process. So in a way, the first step might have, you can say that this actually worked as a template, but technically not. The last phase of my talk, I'll come to after working a lot on this nanostructure for 10 years or so. I got a little fed up because some of the people started talking about, sir, Somnath sir, we are doing just materials engineering, do some very fundamental work. I said, yeah, sure. I'm a physicist by training. So now we changed gear a little bit. Our materials engineering work is going on. We now shifted our focus into understanding the properties of single nanostructures more in depth. So as you can see, this paper came up. It is our last year's work. In fact, during the pandemic time, just before pandemic, the student gathered data, and during the pandemic, we could pull out the manuscript. that we just one single TiO2 nanotube. It is photolithographically made electrodes. Electrodes are, as you can see, just 2 micron separation, and we have put the nanotube as a bridge, as you can see here, SEM picture, and we made a detailed current voltage study to understand the fundamental current voltage conduction mechanism. We have also pointed out for the first time that how much current one single nanotube can sustain, which is called breakdown, not breaking. So that paper came recently in Nanoscale Advances, which has also been selected for Nanoscale Advances hot article collection. It is there. So this paper is actually open access. You can get this paper directly from Nanoscale website, Nanoscale Advances website. And the last work in this thing that is similar, that copper oxide I talked about, you remember? That copper oxide nano wires we took, these are relatively longer. These nanowire, again, we wanted to have that kind of study, how the charge transport happens in a single nanowire. And then also, this also work we have done. We have seen that there is a diameter dependent charge transport, and thicker wire actually has again a CO2O phase. So that thing again coming as a, has a role, although we don't want CO2O, but you cannot avoid CO2O. It comes in traces in mostly in the thicker wires. And that actually, so what we proposed, our hypothesis as that CO2O phase actually acts as a, hole trap. And since CO is a p-type material, hole traps actually reduces the conductivity. So this paper also got accepted earlier this year. As you can see. So this paper just came this year earlier. So a lot of things we are now doing. We are trying to, so one way our materials engineering work is going on. We are now also trying to look at some fundamental physics behind it. Of course, physics is always fun. And so some of the students who got award recently, Saurabh got 2 awards on both this work recently, SRM University Best Oral Presentation, Nanoscale Best Poster Award also he got. Then this is one interview I had given to one Physics World magazine when I was visiting University of Surrey, UK in 2018. This was really a wonderful experience, and out of so many hundreds of delegates, they actually picked up a few delegates from across the continents, and I was one lucky chosen few. And this interview they had put up in their website. With that, I hope I did not upset Sarvanand sir with my timing, maybe a few minutes more, but I hope you all enjoyed. I am available for any discussion. Now, of course, there is no time, but later on. My email is given at the bottom, somnath@iitm.ac.in. I check my email more frequently than I drink water. This is a bad habit, but of course, I live with that bad habit. So the essential point is that you can reach out to me with the email. I will respond pretty quickly. I'm not that big guy that sit on the email forever. Thank you to all my collaborators, my students, my collaborators, my national collaborators, my international collaborators, one of which you have heard with a very exciting demonstration this morning, Professor Saito, Professor Grimes, Karthik also. Yeah, Karthik also you have heard, I think, in this. Particularly Professor Sudha ma'am, thank you all for your support, and all your team, Sarvanand sir, Jayalakshmi madam, Veena madam, Sanju madam, everybody. It's very nice. Thank you.
Thank you. Thank you very much, Professor. Thank you very much for your inspiring lecture on this manner. Okay. So now the session is open to the participants. Participants, if you have any questions, please you can raise the questions to Professor Somnath Rai. Professor, one question is available in the chat box. I will read it. Okay. Why does band gap energy of quantum dots vary with its size? Why does band gap energy of quantum dots vary with its size?
Yeah. So this comes from, I think, from that fundamental, that quantum mechanics. One of the very first lessons that we learned, that is that particle in a box problem. When we have a quantum dot, means essentially is a small shape of the material that is confining an electron. So whenever there is a confinement, we get that band gap enhancement. right? So that particle in a box problem, if you see, you'll understand that it is explained in terms of an electron actually confined in a one-dimensional space. Let's say one-dimensional space. Now that gap between the ground state and the first excited state, that gap increases as this spacing changes. So that concept you can extend. In the 3 dimension, this spacing means the size of the box is what is size of the quantum dot or the diameter of the quantum. So it is one of the most fundamental thing in quantum mechanics that as that spacing changes, you have the gap between the ground state and the first excited. So that ground state and first excited state is the band, in a way you can say. So that is what is.
Okay,
based on the literature, when there is another. Okay, I am reading. Probably I can read.
Okay.
When the electron-hole pair recombinant in fast, the sensor application as response and recovery time is very, very less. For the clarification based on the literature, when the electron-hole pair recombination is very fast, the sensor application as response and recovery time is very less. So I didn't understand. Is the question that electron and hole recombination fast, then response and recovery time is less? Is that the question? I mean, we haven't actually looked at the photo-induced gas sensor, but I think what you are trying to mean is that if there is a fast recombination of electrons, then of course the electrons does not get a chance to interact with anything else. That is what is the point. Can you we can discuss more. You can reach out to me through my email. And there was another question. I could guess carbon. What are the differences between carbon and graphene quantum dot? Practically, technically, I don't. I'm not a graphene or carbon guy. I'm an oxide guy. But what I understand, it's all how you write in the thing. Carbon. When I say carbon quantum dot, is essentially when I say quantum dot, it's actually zero-dimensional thing. Right? Quantum dot is not neither 1D or 2D. It's a 0D. When you talk about graphene quantum dot, I don't see any reason we call it graphene quantum dot. Because when I say graphene, graphene means it's an extended sheet. So there is no point in I am trying to say I have a golden pot made up of stone. What does it mean? It is more uncertainty than that of Schrodinger. I cannot have a golden pot made up of stone. Similarly, I don't find any reason to call graphene quantum dot. It's like carbon quantum dot. So no, maybe I'm wrong, but graphene quantum dot are essentially carbon quantum dot. We cannot call a quantum dot as graphene. Graphene has to be spread 2D, but quantum dot is 0D. So I feel it's my understanding. So there is no difference. The bottom line of the answer is there is no difference.
One more question from my side. The zero dimension, people are talking about this quantum dot is a zero dimension, and they are claiming that it is a nanostructure. But how come a zero dimensional object comes under a nanostructure? Can you explain this?
Yeah, sir. What I understand,
when nanoscale, it's a dimension.
When I say zero dimension is just something for us to understand that it is confined in all 3 dimensions. But if it is a 0 dimension, still, if you say, when I say quantum dot, nanoparticle, whatever, we call it 0 dimension for our understanding and for our to distinguish it from a thin film or a nano rod or something. But it cannot be 0 dimension as such. It has a finite spread in X, Y, Z all direction. Has to be. So 0 dimension is just a conceptual thing, we say. It's a particle. Just a particle.
Okay. Thank you very much. Any other questions from the participants? Okay. If there is no question, let us thank Professor Raj for his informative talk on nanostructure. Thank you very much, sir.
Thank you.
Thank you very much, Dr. Somnath.
Thank you, ma'am.
Thank you so much. It was a scintillating talk. Thank you.
Thank you, sir. Thank you very much, sir. We'll move on to the next session. I request Dr. K. Subramaniam, sir, to introduce our resource person, Dr. Maximi, from the Institute of Applied Physics, Friedrich Schiller University, Jena, Germany, to give the invited talk. Dr. K. Subramaniam, sir.
Yes, ma'am. Am I audible to you, ma'am?
Yes, sir. Yes, sir.
Good afternoon to all here. It's a pleasure to invite Dr. Maxime Chambono, postdoctoral researcher, Institute of Applied Physics, Friedrich Schiller University, Jena, Germany, to deliver a talk on in-volume laser silicon interaction limitations, solution application. I take this opportunity to introduce Dr. Maxime Chambono. He has received his PhD degree at Aix-Marseille University, France in the year of 2014. His research area includes laser matter interaction, silicon photonics, optics. He worked as postdoctoral researcher at LP3 laboratory in Marshall University, France from 2015 to 2016. Currently, he is a postdoctoral researcher at the Institute of Applied Physics in Friedrich Schiller University, Jena, Germany, since 2018. He has published 50 papers in peer-reviewed journals. Once again, I invite Dr. Maxime Chambono to this session. We welcome you, sir. Now you take your space, sir.
Thank you very much for your kind introduction. Can you hear me?
Yeah, I can hear you, sir.
Yes.
Amazing. Then I'll try to share. All right. Can you see my screen now?
Yeah, I can hear you.
Yes.
Amazing. Thank you for your kind introduction. And first of all, I'd like to thank all the committee of ICHSM-2021 for giving me the opportunity to give this invited talk. So today I'm going to talk about in-volume laser silicon interaction, especially the limitations and what has been found so far to unlock some applications. So here is the outline of my talk. In the first part, I will briefly introduce the context about ultra-fast laser silicon interaction. Then I will show how it is possible to hack microelectronic devices with underdense femtosecond laser produced plasmas. Then I will move to some permanent modifications, especially the functionalization of silicon with nanosecond pulses, and also with picosecond pulses afterwards for writing low loss waveguides. And finally, I will focus on some latest results we obtained on semiconductor metal ultrafast laser welding. So first, let us introduce the context. So as you may know, 3D ultrafast laser inscription in dielectrics is a proven technique. And essentially the reason for this is that at the time scale of 100 femtosecond, or approximately, namely it's ultra short laser pulses, then you have an ultra fast energy deposition, which means an important thing, which is that you can distinguish and separate the causes, which are essentially the absorption of the photons, from the consequences, which are the material response. And in this case, it is, well, it's possible to achieve an extremely high degree of control on the modifications you can produce in dielectric materials. With, of course, applications which are numerous in fiber optics, microfluidics, micromechanics, data storage, more recently quantum computing, additive manufacturing, and surgery. So now, why should we intend to do this in silicon now? Well, here are a few answers. First, in terms of fundamental comprehension, it's always nice to improve the understanding of the response of narrow bandgap materials such as silicon under extreme conditions in terms of energy delivery, pressure, and temperature. Also, it's possible to determine some parameters that are difficult to access, such as the ionization dynamics, the plasma recombination, and the electron diffusion. So this is one answer. The second answer is that it would be quite nice for the industry to take benefit of the electrical properties of silicon. To date, there are lithography methods such as silicon on insulator, so SOI, but they are limited to 2D. And if you want to build 3D architectures, you need to do it layer by layer. You need also a clean environment, you need time, and it's quite costly. And on the other side, if one can develop ultra-fast laser inscription inside silicon, it would provide a 3D, flexible, fast, and contactless way to functionalize the material. And at last, for economical reasons, it would be good to extend 3D ultra-fast laser inscription to silicon because of the constantly growing markets of here I give some examples: silicon photonics, quantum technologies, ultra-fast microelectronics, sensors, photovoltaics, and so on. So is it the main question now is it that easy to transfer ultra-fast laser writing to the bulk of silicon? Well, sadly, the answer is no. And if one wants to aim at ultra-fast laser writing inside silicon, one will face different problems. First, they will face technological difficulties because first, the silicon is not transparent to visible light, as you can see here. So you need 4 infrared laser sources. Also associated to this, you need some optics and detectors that are both costly and less efficient in the IR than in the visible. Here I give an example. For instance, your smartphone has roughly a pixel size of 1 micron, while a very good IR camera in gas based is around 10 micron pixel pitch. But if this was the only reasons, then it would be possible to functionalize silicon with a laser. No, the main problem originates from physical limitations, especially when you look at the nonlinear refractive index of silicon. It is about 100 times higher than the one of fused silica, which means that during the propagation of the laser pulse, there will be a competition between Kerr effect on the one hand, which focuses the beam, and plasma defocusing on the other hand. So you focus the beam, the material starts to be ionized, and this ionization provokes a defocusing, which is called plasma defocusing. In other words, we are in the filamentation regime, which is a highly nonlinear propagation regime. I would not say the word chaotic, but you get the idea, I hope. And there are 2 consequences to this. First, as illustrated here, there will be a nonlinear defocalization. Here you can see that the focus is unambiguously shifted upstream towards the laser. Second consequence is a saturation of the intensity inside the bulk of the material, which is illustrated here, which means that when you take those 2 consequences together, there will be a delocalization of the energy deposition in the prefocal region. And as a consequence of this, one can conclude that increasing the laser energy will be a bad strategy for hoping to modify silicon and with ultra-short laser pulses. So first, let me introduce how we can use the underdense plasmas that are produced with femtosecond laser pulses for hacking microelectronic devices physically. But first of all, I have to recall some basic operations of microelectronic devices. Here I take the the example of a MOS flash memory, which is defined by 2 logical states, essentially, the erased and the programmed states, so 0 and 1, which depends on the number of electrons present in the floating gate represented here. For basically erasing the flash memory, one can use negative voltage here and zero elsewhere, and the electrons will be repelled towards the bulk, so the silicon substrate. Then afterwards, one can read the drain current as a function of the gate voltage, which is nothing else than a characteristic curve for stating 0 or 1 for the logical state of the device. And then if one wants to program the flash memory, you put basically 0 volts in the source and the drain, and in the source and the bulk, then a positive voltage to the drain and the control gate. And what will happen is that some electrons will migrate from the source to the drains, and some of them will be crossing the tunnel outside. And then when you read the device, you have this characteristic IDVG curve. One can also define the threshold voltage, which is the voltage for which the drain current is 1 microampere, and it quantifies the charge of the floating gate. So now the main question is that possible to emulate this process with laser radiation? To answer this, we have developed an experimental setup. I will not go too much to the details, but it relies on laser pulses, ultra-short laser pulses, so 100 femtosecond at 1.3 micron wavelength. Then we control the energy by means of a half-wave plate and a polarizer, focus the beam to the microelectronic wafer. And besides, we have two diagnostics. First, a stereo microscope in order to make some 4-point probe measurements and eventually program and erase the device in situ. And also here in green, represented in green, sorry, a microscope working in reflection for observing the microelectronic device and induce the plasma near the flash memory. So then when you perform some laser irradiation of the flash memory, here are the results. So you start here in solid blue and red lines, either erased and programmed. And you can see that there is clearly an effect of the laser radiation after 10,000 shots and 1 million shots, which means that there is a migration of particles, either electrons or holes, from or towards the floating gate. Then when you repeat this for different number of shots, here I represent the threshold voltage as a function of the number of shots, and you can see that the laser-induced programming and erasing phenomena are saturated somehow around, here it's around 5 volts. Interestingly, the curve describing the laser-induced programming and erasing follows the following function. So a sigmoid function as a function of the number of shots. That can be written like this, where A, B, and C are three free parameters. A and B are related to the boundary conditions, and C is the speed of the sigmoid curve. So the whole game here will be to determine what are A, B, and C. But first, how can we explain physically this kind of laser-induced programming? So let us consider the device and the associated Venn diagram. So the first mechanism occurring is the laser propagation, of course, which leads to the formation of a plasma in the silicon part by two-photon ionization. Here is represented the two-photon absorption. Then some electrons will be able to tunnel through the oxide layer toward the floating gate. Then this increase in the negative charge will lead to a change in the Venn diagram. And finally, the electrons and hole pairs that have been produced in the silicon substrate will recombine, and in the end you have more electrons in the floating gate than initially. And by repeating this from one pulse to another, you can clearly see that no electron migration will be possible once the band diagram will be completely flat. So in order to test this theoretical scenario, we have carried out 2 experiments. So the first experiment consists in using a control gate voltage, which is called polarization or bias. And here you can see the threshold voltage as a function of the number of shots for initially erased and programmed flash memories. And one can see that by having different bias, you can play on the final state of your laser-induced programming, which means that adjusting the polarization enables us to control the asymptotic VT value. This is consistent with the proposed scenario because the polarization will modify the initial band diagram. And we'll also observe the linearity between the threshold voltage and the applied bias. This allows us to determine A and B in the sigmoid curves, so the two of the 3 free parameters, which are related to the boundary conditions. So now we just need to evaluate what is C and how it can be related to the laser parameters. In order to do so, we have evaluated the influence of the laser energy, as you can see here. So same kind of graph, the threshold voltage as a function of the number of shots. And one can see that for low energies, the parameter C increases with the input pulse energy, so the laser energy, which is consistent with the 2-photon ionization mechanisms, because the more the energy, the more the ionization, of course. One can also note that at high energies, there are some chaotic behaviors after a few shots, which are related to the degradation of the drain bulk and source bulk junctions. So here is the take-home message for this part. It is possible to hack physically microelectronic devices with infrared laser pulses. The polarization allows to control the asymptotic threshold voltage, and the laser programming speed depends on the pulse energy. So now a second study was oriented on the functionalization of silicon with nanosecond pulses. Why? Let us, well, summarize and evaluate the pros and cons of each regime. In the femtosecond regime, as we have seen, a low pulse energy is needed, and it is suitable for handling free carriers in a non-destructive way in microelectronic devices. However, the cons are, of course, it's impossible to modify the material inside the bulk. This is due to strong nonlinear propagation effects. But then if you go to the nanosecond regime, so 1 billionth of second, then it has been shown that it is possible to modify permanently the bulk of silicon. And this is due to the fact that when you increase the pulse duration, you decrease the intensity, and thus you decrease the nonlinearities inside the material. However, of course, more energy will be needed, and the main drawback is that you cannot separate, as I said in the introduction, you cannot separate the causes and the consequences, and thermal effects will occur during the pulse, which will lead to a high heat-affected zone. So in order to investigate the influence of nanosecond pulse irradiation inside silicon, we have developed another setup relying on 1.55 micron wavelength pulses at 5 nanosecond duration. Then, same as previously, we adjust the pulse energy with a half-wave plate and a polarizer, and we use the same microscope for positioning the geometrical focus with respect to the sample. And besides, we have another diagnostic, which is represented here, which is nothing else than Mach-Zehnder interferometer, which allows us to, well, it is at least transposed to the infrared at 1.3 micron wavelength, and it allows us to have phase images. So what is the phase shift of the laser-induced modifications, which are, well, essentially related to the refractive index change. Then here are some typical results we obtain when one tries to inscribe some lines inside the material at different scanning speed, so different feed speeds. What one can see is that for high and low speeds, you can see some black dots in the phase images, which are related to some negative phase shift, meaning that there are some negative index change, which have to be related to voids or microcavities inside the material. In stark contrast, when the when the writing speed is intermediate at 0.1 millimeter per second, one can see that there is no black dot in the line, and we have inscribed the structures as we can inscribe lines with a positive phase shift, meaning that there is a positive refractive index. The possible mechanisms for this are that the melted material induced by one pulse will fill the voids left by the preceding ones, meaning that in the end, when the material resolidifies, there are strong strain fields inside the material which provoke a refractive index change. And if one wants to evaluate the refractive index change, it's given by this expression here, and we find that it's on the order of 5 times 10 to the minus 3, which is theoretically sufficient for guiding light. So now the main question is, can we really guide light inside silicon? That would be a wonderful achievement, and this is what we endeavored. So here you can see a shadow graphic image of the written line. We have injected some infrared light inside the structure and detected the scattered light. And besides, we have carried out here in C and D some evaluation of the linear propagation in silicon, if one assumes that there is no guidance. So first, we can evaluate the numerical aperture of the potential waveguide, which is around 0.2. And the injection of the light with a high numerical aperture objective will allow us to have a strong divergence. So it's easier for us when we use a numerical aperture, which is much higher than the one of the potential waveguide. It is much higher. It is much more convenient to see if light has been guided. And from the scattered light picture here, you can see that one can clearly see that some light has been guided, especially when you compare to the linear propagation calculations. So here are this is indeed the comparison between B and C. And you can see that in the experiments, there is more light than normally if you consider only free propagation inside silicon, meaning that part of the light has been guided. Especially, this is a semi-log scale, which means that the experiments are 100 times higher than the free propagation calculation. So in the end, light has been indeed guided with high losses. I will come back to this afterwards, but still, it's a first step. Then, then with this positive refractive index change, it is possible to find some applications in the field of refractive index engineering for writing millimeter-long waveguides. as you can see here on the left, multiplexers for splitting and coupling the light, also called Y-couplers. We have inscribed diffraction gratings, and also we have performed surface texturings, either with negative index change or the positive index change corresponding to the waveguides, where we see some micro pyramid on the surface of silicon after selective chemical exchange. So here is the take-home message for this part. So with nanosecond pulses, we have decreased nonlinearities, meaning that it is suitable for modifying silicon in the bulk. It was possible to inscribe continuous lines of positive refractive index change. The refractive index engineering endeavors allowed us to demonstrate that it is possible to write long waveguides, multiplexers, and diffraction gratings. However, the losses were relatively high. And this is one point we addressed afterwards by endeavoring some picosecond laser irradiation for waveguide writing inside silicon. So here, the idea is to drastically decrease the losses, the damping losses of the waveguide, and well, access to some new applications. Here, the motivations are, well, are formulated in terms of questions. Like first, is it possible to write low loss waveguides inside the silicon with picosecond pulses? Because it's the intermediate regime between nanosecond and femtosecond. So it would be nice to investigate that. Then if it is the case, what is the refractive index change? And moreover, what's the origin of the waveguiding? So to answer this, experimentally, we have another setup relying on 1.55 micron wavelength at around 0.8 picosecond duration. Then classically, the beam is focused in the bulk of silicon. We have also one transverse microscope here represented, relying on white light emission and detected with an objective lens, a tube lens, and a camera, an InGaAs camera. Besides, we have another microscope here in green for positioning the focus with respect to the entrance surface, as you can see here. And with the first infrared microscope in a transverse way, one can, I hope it will start, yeah. So the idea is to write the waveguides from the back surface and move the focus towards the laser. So to take advantage of the brittleness of the exit surface. The typical processing parameters are a feed speed of 20 micron per second and pulse energy around 100 nanojoules. Concerning the waveguide characterization afterwards, so this is done post-mortem. We have employed another setup which relies on the emission of a continuous wave laser diode at 1.55 micron wavelength. Then the beam is focused to the waveguide and detected with a similar infrared microscope working in transmission as previously. And also we have another microscope allowing us to distinguish the scattered light. So here is typically what you see with the scattered light. So the damping losses can be estimated with this. And with the InGaAs microscope working in transmission, you can see the mode field and near field images. So what we concluded on those measurements is that we had some coupling efficiency of around 53%, a transmitted power of around 25%, which is consistent with the value we obtain from the scattering images. And moreover, the damping losses are around between 4 and 5 dB per millimeter, which is much lower than what we had before with the nanosecond pulses. Again, it was possible to demonstrate some functionalization of the material with a Y splitter, so a multiplexer, which is actually an additional proof of the light guiding. Here you can see the beam before it enters the waveguide, and here is the near field image, which corresponds to the measurements, and you can clearly see two different spots corresponding to the two different parts of the Y coupler. So the splitting ratio was 50-50, and here again the damping losses were 4 to 5 dB per millimeter. Concerning the refractive index change, we have estimated it by coupling theory with Helmholtz equation and overlap integral, and also, as you can see here on this video, some shift measurements that are detailed in a recent paper from our group. So the reference 2 here on these slides, which allow us to conclude that the waveguides are W-shaped, meaning that you start with a negative refractive index, then a peak of positive refractive index. And the maximum refractive index in this case is around 2 times 10 to the minus 3. And this is in good agreement with highly confined modes. So in the end, we have a single mode waveguide with low losses. Also, one could wonder what are the physical mechanisms related to the waveguide inscription in this case. And to answer this, we have carried out some material characterization at the nanometer scale with transmission electron microscopy and for different input pulse energy. What we saw is that clearly in the path of the waveguide, there are some local defects, which could be dislocations. However, the density of those dislocations does not depend much on the laser energy. And by performing electron diffraction, so selective area electron diffraction, we have noticed that there is actually no change, surprisingly, in the crystal structure of the material, which means that those waveguides may rely on strain induced by the presence of dislocations in the monocrystalline silicon. And here is the take-home message. First, we have demonstrated the exit surface seeded inscription of waveguides with picosecond pulses. The waveguides are low losses and the refractive index change is higher than 10 to the minus 3. And the nanometer scale analysis allowed us to claim that some strain was induced by the dislocations provoked by the laser pulses in the monocrystalline material. And finally, I would like to talk about our latest results, which basically are related to the comprehension of the filamentation inside silicon with picosecond pulses for semiconductor metal ultra-fast laser welding applications. So this is a kind of a hot topic in the laser processing community. To focus first on the context, ultra-fast laser welding is, the context about ultra-fast laser welding. Well, so first, joining materials is something essential for manufacturing, additive manufacturing for different industrial applications. And to do so, some traditional methods may be used, such as adhesive bonding, brazing, anodic bonding, and so on. However, those methods usually I mean, usually they show some important drawbacks. For instance, they may require another material or pressure assistance, or maybe they will face some aging or degazing problems, or they might just be not, the joint materials will be not too resistant enough to high temperatures. As a quite nice alternative, the laser welding technique has been developed, which consists of an energy deposition at the interface, as illustrated here, and it provides a fast, clean, and contactless way to join materials with a high strength between those. It was shown to be applicable in different material configurations, such as glass-glass, glass semiconductor, glass-metal, polymer-polymer, and more recently, ceramic-ceramic, as demonstrated in this science paper in 2019. However, in the semiconductor metal configuration, there is nothing too convincing so far. So let us have a try together. Well, to do so, we'll employ the following setup, which again relies on 1.55 micron wavelength and around 10 picosecond duration laser pulses. Then we adjust the energy classically with a half-wave plate and a polarizer before the beam is focused at the interface between silicon and copper by means of an objective lens. And this objective lens is also part of a reflection microscope, which enables us again to position the geometrical focus with respect to the silicon entrance surface. Then after the laser processing, we evaluate the bonding quality in a post-mortem way by separating the two samples with an indenter. And when we try with a relatively intermediate, let's say, input pulse energy of 300 nanojoules, then we can measure a shear joining strength of 30 kilopascal. Okay. Then what happens if we double the input pulse energy and go to 600 nanojoules? Then the shear joining strength is 3 times lower, 10 kilopascal. Okay, so this is weird, but the main question is that sufficient? And sadly, the answer is no. Actually, in this case, the two materials are easily separable by hands, while typical values obtained for other material configurations or traditional bonding methods are on the order of 1 to 20 megapascal. So now we have to explain why. And when one wants to explain that, one has to recall that silicon is a medium where the propagation is highly nonlinear. For the reasons I mentioned previously about the nonlinear refractive index, which is 100 times higher than the one of fused silica, meaning that, for instance, let me give you an example. If you consider 1 microjoule input pulse energy, which is pretty typical, is the good order of magnitude for laser processing applications, then the peak power will be higher than the critical power for self-focusing for pulse durations below 20 picoseconds. And this value of 20 picoseconds is extremely high. And thus, as previously described, there will be this competition between Kerr effect and plasma formation together with defocusing, leading to the formation of a filament. Then the two consequences, I already talked about this. And again, there is a strong depletion of the energy deposition at the exit surface of silicon. So actually the interface between silicon and copper in our case. So the solutions we propose is, first, we use an interface with a metal, meaning that the absorption will be drastically increased, which is pretty good. And second, we propose a filament relocation method to get an increased intensity at the interface between silicon and copper. But to do so, we need for nonlinear propagation imaging, and this is actually exactly what we did. We imaged the nonlinear propagation inside silicon by means of this setup, which is nothing else than an inverted microscope. And it allows us to evaluate experimentally the 3D fluence distribution inside silicon for different input pulse energies indicated here, and thus the nonlinear focal shift delta Z as shown here as a function of the input energy. In this data, 3 regimes can be distinguished. The first one for low pulse energy is, of course, the linear propagation regime as confirmed by point spread function analysis. If you want more details, you can check out those 2 references. This is a paper which will be soon published, and this is the corresponding software which is open access. So I really encourage you to check this out. Then for intermediate pulse energy, up to 100 nanojoules, we can see that the focus is unambiguously shifted from the initial position in the linear configuration. However, the shape is conserved in this case. And the last regime for more than 300 nanojoules is that we are in the filamentation regime, sorry. And here you can clearly see it with the focusing and defocusing dynamics. So the conclusion of this is that increasing the input pulse energy will lead to an energy deposition far away from the interface, which is in good agreement with a semi-analytical model we have developed. You can check the corresponding papers I will give afterwards in the next few slides. So the question now is, can we push even more the limits? Well, to answer this, here I represent the shear joining strength between the silicon and copper for 2 input pulse energies, without in red and with in green precompensation of the nonlinear focal shift. And the striking feature from this figure here is that precompensating the nonlinear focal shift leads to a much better welding. Okay, so now the main question is, can we simultaneously keep this precompensation of the nonlinear focal shift delta Z strategy and increase the input pulse energy to get even more energy deposition at the focus? And the results are essentially shown here in the bottom. So the shear joining strength as a function of the input pulse energy, and you can see that around 1 microjoule input pulse energy, one can reach around 2.2 megapascal shear joining strength, which is quite suitable for applications. And the reason is that when you precompensate the nonlinear focal shift, you increase the maximum fluence at the interface, as well as the energy deposited at this interface. I mean, the energy reaching the interface, sorry. Then we observed, I mean, noteworthy, like here in purple is the nonlinear propagation threshold, and one can see that no welding is possible between silicon and copper for input pulse energies below 100 nanojoules, meaning that silicon to copper ultrafast laser welding is solely achievable in the filamentation regime. So you got, if you want to do this, you got to, well, take into account the nonlinear focal shift and the filamentation. So here is the take-home message. So we demonstrated the first semiconductor and metal ultrafast laser welding because we characterized the filamentation induced by picosecond laser pulses inside silicon. Besides, we have demonstrated that megapascal shear joining strength were achievable, which are compatible with applications. If you want more details, you can scan this QR code here, which will lead you to our latest publication on the topic, which made the cover of Laser and Photonics Reviews a few weeks ago. So, to summarize, we can draw the following conclusions. In the femtosecond regime, in-volume laser direct writing in silicon is intrinsically limited by filamentation, which prevents the production of permanent modification inside the material. However, the produced underdense plasmas can be utilized for hacking microelectronic devices. And then in the nanosecond and picosecond regimes, the lower intensity leads to lower nonlinearities, and it is possible to modify and thus functionalize silicon with the inscription of optical elements inside the material for guiding, splitting, and dispersing light, for instance. And the best is yet to come, let's say. Also, the understanding of the nonlinear propagation inside silicon, especially the filamentation regime inside silicon, allows developing novel applications like semiconductor and metal welding. Before ending my talk, I would like to acknowledge some of my colleagues, especially my former supervisor in LP3 Marseille, David Grosjean, the group of Shooting Lay in Manhattan, Kansas, USA. Some of my colleagues from IM2NP concerning the microelectronic, studies. My colleague Stelios Tsortsakis from Forth in Greece, which did a lot of he did a fantastic job concerning the simulations for a better understanding of the filamentation regime. Of course, all my colleagues at IAP from the group from Stefan Nolte, so Markus Blotte, Qingfeng Li, Alessandro Alberucci, Chandrot Jisha, Helena Kammer, and Gabor Mateus. And finally, the postdoc of Stelios Tsortsakis, who work at Texas A&M in Doha, Qatar, Vladimir Fedorov. So I'd like to thank all of them. And also, I would like to thank you for your attention. And ultimately, if you want more information, you can scan this QR code where you will see all the associated publications that I've shown today. And also you can alternatively contact me anytime at my address, so my professional address at the University of Vienna. Thank you.
Thank you, Dr. Maximi, for delivering a wonderful presentation. It's really amazing. So you have unearthed so many facts related to the lasers, and it's got this amazing performance. So
thank
really
you.
Wonderful. So behalf of the SRMIST Ramapuram campus and my own behalf, I would like to thank you for your spending your valuable time in our session. So now I call the audience to interact with the Dr. Maximi Chambano. You can ask your question. The audience, you are encouraged to ask the questions to Maximi. Any questions from the audience side? Dr. Maximi, sir, we have a few questions in the chat box. So,
let me check. So maybe I should share. Oh, okay. Yeah. Wow. Thank you all for your comments. So question about the dB, which is decreased to 4.5. What is the lowest losses that can be reached at least? The dislocation does not the crystal structure. So what is the origin of the dislocation? Dislocation does not modify the crystal structure. Okay. So concerning those dislocations, it's just that some atomic planes will slide up. One atomic plane will jump above the other. So actually, there is no change in the crystallinity. However, there will be some reorganization. And concerning your first question, what is the lowest losses that are achievable? Well, to date, these 4.5 dB per millimeter are the lowest losses that can be achieved in silicon. Well, the lowest losses achieved in silicon with laser inscription technique. As I said before, you can check the publication of, I'm thinking about Professor Michel Lipson, working in the US in New York, who works on SOI, so silicon and insulator, and of course they achieve much lower losses. However, the SOI technique, as I said, it is not that convenient. It is really powerful, but we got to find some alternative, and this is the philosophy of my work, actually.
Okay. My question is, what is the purpose of making the wavelength lambda by 2 before the writing? In most of the slides I have watched that you have mentioned that the lambda by 2 after that. What is any special purpose for making that wavelength by 2?
So yeah, so sorry, this is so lambda by 2 means half wave plate. So this is a plate which allows to change the polarization direction. And when you combine it with a linear polarizer, it acts as a filter, like a tap, but for the laser energy. And then you can precisely adjust the laser energy.
Yeah, but what is the purpose of putting that that halfway plate in front of that?
Well, when you combine it together with the polarizer, so you rotate the polarization and then you filter some polarization. So it's not that you divide the wavelength. It's just that you rotate the polarization. It's called lambda over 2 half wave plate, but there is no frequency conversion, like no nonlinear crystal. It's just some birefringent plate which allows to change the polarization orientation for adjusting the power.
Okay. Audience, do you have any question to Dr. Maxime, sir? Audience? Okay, thank you very much. Please stay with us, sir, for the validatory function. Please stay with us.
Thank you.
Thank you.
Hi,
Thank you.
Maxime. Hi, Maxime. Thank you so much for delivering a wonderful lecture. Please, within a minute, we will start a validatory function. Please join us.
Sure.
Please be in this meeting. And good evening, Professor Mohammed Joini.
No, it's okay. I asked 2 questions and I have got their answers. Maybe one. It's a nice talk, and I'm not physicist, but I really understand.
Yeah, we saw your message.
Yeah, thank you.
Please be in the meeting for 10 more minutes.
Yeah. Okay. Thank you.
Good morning, sir. The Dean Research Sir joined.
Good evening, sir. Dean Research Sir.
Good evening, madam. Good evening.
Good evening, sir. Sir, Professor Mohammed Joini from University of Paris, France.
Yeah.
And
yes. Good evening, sir.
Yeah, thank you very much for this nice conference and for all these meetings we get these 3 days. I have not been present all the time. I'm sorry, because I had some medicinal checkup. But I was really very happy to join all of you and to be with you during all these sessions. And I would like to thank all of you for this nice job, nice conferences, and really nice meeting. Thank you. Thank you very much.
Thank you, sir. Thank you.
please be in the meeting, Mohammed Joini, sir.
Sorry?
And Dean Researcher Dr. Maxim Chemana is also there. He is from University of Jena, Germany.
Good evening, sir. Good evening.
Maxim.
Thank you. Thank you.
Yes.
Good evening, sir. How are you?
Thank you. Thank you. Okay. We cannot get inside the poster session. Can we go to the poster session by video?
Yeah, sure. We will send. We will send by mail.
Okay.
Sure.
Thank you very much. Thank you.
Veena ma'am.
Have a good time and thank you very much.
Please be in the meeting for 10 more minutes.
Sorry?
Please be in the meeting for 10 more minutes. 10 minutes. Please be here in the meeting.
You want I be where?
Professor Juini, please be in the meeting for 10 minutes.
For 10 minutes?
Yeah.
Yeah, I am here.
Yeah,
Yeah, I'm here. When I am here, but I'm sorry. Yesterday I wasn't all the time here, so sorry.
I welcome you all for the valedictory function of the Virtual International Conference on Hierarchically Structured Materials, ICHSM-2021, organized by Department of Physics, SRMIST, Ramapuram Campus, Chennai. Now I request Dr. L. Sudha, Professor in Department of Physics and also the convener of the conference to give the welcome address. Ma'am, please.
Respected Dean ENT, sir, and respected Dean Research, and Professor Mohammad Juini, and Dr. Maxim Chambone from University of Jena, Germany, and my dear participants, good evening to one and all. I take privilege in welcoming everyone for this valedictory function. Thank you.
Thank you, ma'am. I take immense pleasure to share the report of the conference, Virtual Conference 2021. We have started the session of day one with our chief guest, Dr. Chandrabas Narayana, Director, Rajiv Gandhi Center for Biotechnology, Government of India, Thiruvananthapuram, Kerala. He has given a keynote address. And the next session with the Professor Mohammad Juini from the University of Paris, France. He has given a talk on organic and inorganic hybrid electrode materials for photoconversion of solar energy. We had a plenary session with Dr. Claudia L. Bianchi, professor from University of Milano, Italy, and Dr. S. Kumar, professor and director of National Center for Science and Nanotechnology, University of Madras, have given a talk on hierarchically structured materials, inevitable replacement in the field of healthcare and hydrogen production. We also had Professor Sanjay Mathur, a director, Institute of Inorganic Chemistry, Chair Inorganic and Material Chemistry, University of Cologne, Germany. He gave a talk on efficient photon harvesting technologies for water splitting reactions. And in the second day of our conference, we have started with a plenary talk with Dr. Oman K. Varghese, Associate Professor, Department of Physics, University of Austin, Texas. The next talk was Dr. Karthik Shankar, Professor, Department of Electrical and Computer Engineering, University of Alberta, Canada. He gave a talk on 2D carbon-based semiconductor nanomaterials. And we had a talk with Dr. Yashura Hayagawa, Professor, Suzuoka University, Japan. He gave a talk on synthesis of photosensitive nanoparticles for bioimaging and diagnostic applications. Dr. Masaru Shimomura, he gave a talk. He is from professor from the Suzuoka University, Japan. He gave a talk on element-sensitive local structural analysis by X-ray fluorescence holography and photoelectron diffraction. An invited talk by Dr. Mukesh Kumar, Associate Professor, Functional and Renewable Energy Materials Laboratory, Department of Physics, IIT Ropar, Punjab. And we had a talk by Dr. Kumar Raju, a Senior Researcher, Energy Center, Council of Scientific and Industrial Research, South Africa. In the third day, Dr. Mohammad Faiz bin Mohammad Salik, Senior Lecturer, University of Malaya, Malaysia. He gave a talk on thermoelectric power factor of rutile-phased TiO2 thin films. A plenary talk was given by Dr. Nobuo Saito. He gave a very detailed demonstration about remote controllable analytical equipments, TEM and XPS in NUT, Japan. And invited talk of Dr. Raja Bhubati Mani. He is from the department Aalto University, Finland. He gave a talk on mesocrystals, nanoparticle as building blocks in single crystals. and an invited talk of Dr. Somnath Roy, Associate Professor, Department of Physics, IIT Madras. He gave a talk on beautiful world of one-dimensional nano and heterostructures. And Dr. Maximi from the University of Jena, Germany, he gave a very detailed and informative talk in volume, laser silicon interaction, limitations, solutions, applications. And we have received more than 230 abstracts from all over India and 23 abstracts from foreign universities. Contributory sessions were conducted as a parallel session for oral as well as poster. We have received, there were 73 oral presentations and 86 poster presentations. Participants actively interacted with the resource persons, and we have received a very good feedback, a positive feedback from all the participants. Thank you. Now I request our Dean Research, SRMIST Ramapuram campus, to give the valedictory address. So please.
Good evening to all. Respected professor from France and Germany, dear Dean Engineering and Technology, HOD Physics, Dr. Sudha Madam, all the faculty members, and dear participants. This conference is being organized every year, but this year is very special for this conference because the organizers have brought the best resource person around the world. Maybe we have to thank COVID for that. If not, definitely this eminent people, we may not have met them through. And this online platform was very wonderful, and all the lectures which were organized are practically applicable for various applications. I hope all the participants might have got immense and in-depth knowledge in the specialized areas where that is the eminent personalities in the world has spoken about what is the application. Once again, I wish to thank HOD Physics, Dr. Sudha Madam, Dean Engineering and Technology, and all the faculty members of Department of Physics for giving a wonderful opportunity for all the participants to learn in what we call in 360 degree about all the fields what they have chosen. And I hope everybody who have attended this transfer this knowledge, whatever is learned, to the fellow faculty members and also to the students for better development of materials. This hierarchy materials has various application, and the Department of Physics has chosen the right topic, and every year they conduct it, and every year they will organize the best. But this is the best conference. Unfortunately, I was not able to attend because of other assignments in another campus. Thank you very much. Thank you for the opportunity. Thank you. Thank you all.
Thank you, sir. Thank you for your motivating and inspiring speech, sir. Thank you, sir. Now I request Dr. V. Jayalakshmi, Assistant Professor, Department of Physics, to announce a certificate of appreciation for oral and poster presentation. Jayalakshmi, ma'am.
Yeah, thank you, ma'am. Good evening to one and all present here. Now I'm going to announce the certificate of appreciation for oral presentation by Rajapreeta, Anna University, Crystal Growth Center, Priyanka Bomalu, Down University, Dehradun, and Pradeep Kumar Sharma, IIT Delhi, Dr. Veslin Vedakumari, Chettinadu Academy of Research and Technology, Kelambakam, Sutapa Dev, IIT Delhi, and K.S. Kiran from Jain University, Bangalore. Now, the certificate of appreciation for poster presentation are Mr. Ashwin, Department of Physics, DG Vaishnava College, Chennai, Ms. Sebandi, Department of Physics, Satyabama Institute of Science and Technology, and Ms. Christina Jabraj, Department of Physics, Science and Technology. Thank you, one and all.
Thank you, ma'am. Now I request Dr. M. Saravanan, Assistant Professor, Department of Physics, to propose vote of thanks. Saravanan, sir.
Yes, madam. Respected Dean ENT,
respected Dean Research and Professor Mohammed Joini, Dr. Maxim Champani, faculty members, research scholars, and students of various institutions.
Veena ma'am.
Sir, Saravanan sir, you're not audible, sir. Saravanan sir. Sir, you're not audible. Saravanan sir.
Veena ma'am.
Yes, ma'am.
Veena ma'am.
Yeah, 1 minute, ma'am. Saravanan sir.
Yes, madam. Yes, madam.
Yes.
Sorry. Yes. I'm audible, madam.
Yes.
Yes, yes.
Respected Dean NT, respected Dean Research, and Professor Mohammed Joini, Dr. Maxim Champani, faculty members, research scholars, and students of various institutions. A very good evening to all present here. It is my privilege to propose a vote of thanks amidst the gathering. First, I'd like to thank to our chief guest of this virtual international conference on hierarchically structured materials, Professor Chandrabas Narayana, Director, Rajiv Gandhi Center for Biotechnology, Government of India, Thiruvananthapuram, Kerala, for his august presence and giving consent to deliver the keynote address during the inaugural function. I'd like to thank Professor Yashiro Hayakawa, Shizuoka University, Japan, and Professor Mohammed Joini, Head of NMS, Université de Paris, France, for their august presence in inaugural function and giving consent to deliver the opinion talk on this conference. Next, I'd like to thank Professor Nobuo Saito, Deputy Director, Analysis and Instrumentation Center, Nagakuwa University of Technology, Japan, for his live demo. Professor Claudia L. Bianchi, Università degli Studi Milano in Italy, Professor Masaru Shimamura, Professor, Shizuoka University, Japan, Dr. Mohammed Faiz bin Mohammed Saleh, University of Malaya, Malaysia, Dr. Maxim Champani, Friedrich Schiller University, Jena, Germany, Dr. S. Balakumar, Professor and Director, National Center for Nanoscience and Nanotechnology, University of Madras, and Dr. Rajabhupati Manigandan, Aalto University, Finland, Dr. Mukesh Kumar, Associate Professor, IIT Roper, Dr. Somnath Chandra Roy, Associate Professor, IIT Madras, Professor Sanjay Mathur, sir, Director, Institute of Inorganic Chemistry, University of Cologne, Germany, Professor Karthik Shankar, Professor, University of Alberta, Canada, Dr. Ganesh Kumar Mani, Micro Nanotechnology Center, Tokai University, Japan, Dr. Uman K. Varghese, Associate Professor, University of Houston, Texas, and Dr. Kumar Raju, Senior Researcher, Energy Center, Council of Scientific and Industrial Research, Pretoria, South Africa, for giving consent to deliver the plenary and innovative talk of this conference. I'd like to thank our Honorable Co-Chairman, sir, to deliver the presidential address in inaugural function. Next, I would like to thank Vice Chancellor, SRMIST, to deliver the special address in the inaugural function. I'd like to thank our Director, SRMIST Ramapuram Campus, to provide constant support to conduct various events in our department. And next, I'd like to thank our Dean ENT, sir, for his valuable support and the proper guidance to conduct this conference in successful manner. Thank you so much, sir. Finally, I'll thank Dean Research, sir, to deliver the valedictory address. Finally, the last but not least, I'd like to thank our faculty members, research scholars, participants, and students from various institutions to bring out this conference a grand success. Thank you.
Thank you, sir.
Thank you all.
You can mute now. Feedback shared. Sanjay, yes, ma'am.
No, you carry on.
Sanju ma'am, please share the feedback link, ma'am.
I'm sharing.
Thank you, Dean Research Sir. Thank you, Dean ENT Sir.
Dear participants, the feedback form we have posted in the chat box. Please fill that. It will count toward your attendance while we are giving certificate for attending the conference and participation.
Dear participants, please fill the feedback form that has been shared in the chat.
Professor Maximi, thank you. Thank you for your participation. Thank you. Thanks a lot. Thank you.
Thank you.
Dear participants, once again, we have posted the feedback link in the chat box. Please fill that.
Dear participants, thank you very much for attending our conference. Please fill the feedback form.